jasný ten program, kdo bude vystupovat teď v průběhu, protože tam je to tak nějak všeobecně. Dobrý, a vám to se nemůže
no může, ty to máš vlastně v té podstatě, tam už promítnout ty.
Akorát došlo k drobný úpravě.
Dobrý, to je, nevím, jestli spíš jedná o ten poslední.
Jo, tak to tam promítnu vlastně čtvrtou a pátou, tam dej to.
Já si to cvaknu na telefon.
No, to je bohužel, si dají na to programu, ale tím, jak to napočítá.
Nemění, je to jasný, tohle to musíte tisknout minimálně 2 měsíce dopředu.
No, ale vždycky ještě týden dopředu.
Až takhle máte starý.
No, ale i přesto tam jsou změny.
Chápu, proto je
Dobrý den, pane Fischere. Doufám, že mě slyšíte.
No poslední je čas, no to je nevím, ale to první bych chtěla teda.
Já u vás vidím jenom kameru zaplou, ale mikrofon bohužel nevidím. Jo, tak už se objevil i mikrofon.
Dobrý deň, počujeme sa?
Jo, už vás i vidím a i slyšíme vás tu.
Haló?
Ano?
Dobrý den, slyšíme se?
Dobrý den. Jo, slyšíme všechny, i pana Běláče, i pana Fischera.
Výborně, takže takhle přes audio. A jak je to teďko s mutováním? To se můžu mítnout normálně v obrazovce, když jsem přes telefon připojil?
Jo, to můžete. Nebo vás tu můžu mutnout já.
Ne, protože já teď přemýšlím jenom, jak to vyřešit, teda, že když to nechám běžet, tak jestli...
No, jenom jakoby, podle mě, když jenom dáte mute, tak si vypnete ten mikrofon a pak ho zase můžete zapnout.
Jo, no, já tomu rozumím, že když mi to v tom počítači, když se připojím, jo, už to tady vidím, jo, tady.
Jo, teď to máte zamutovaný. A ještě vás teda zkusím takhle vyzvat.
No, haló, teď mě slyšíte?
Jo, teď vás slyším. Takže to
jo, a
funguje
předtím teda
tak,
jste mě neslyšel, takže to funguje, takže se můžu se zmutnout sám.
Jo,
Jo, a vy mě pak můžete... Dobře, takže ten hovor můžete ukončit telefonní asi, protože jo já
ukončím.
Jo, dobrý, díky moc.
Dobře, tak zatím nashledanou.
Zatím nashledanou.
Ještě jestli s vámi, pane Fischere, jestli se vy mě slyšíte v pořádku?
No, áno, počujem, trošku slabšie, ale...
Jo, tak a my vás slyšíme dobře, takže by to mělo snad fungovat všechno.
Potom prezentáciu si vlastne dávam ja, áno?
Ano.
Cez...
Já zastavím naše sdílení a teď byste to měl mít volný.
Dík. Čiže takto by to malo byť vidno, áno?
Jo, vidíme to tady dobře. Slyšíme vás a prezentaci taky vidíme, takže to je... To je v pořádku.
Dobre, a je to dostatočne veľké?
Jo, já to tady vždycky stejně zvětším, takže to je vidět dobře. To,
Dobre, lebo dal som to do PDF, aby náhodou to nerobilo problémy.
jo.
Čo neposúva. Dobre.
Všechno běží jak má.
Dobre, čiže my potom začíname tých 11:30, áno, naše prezentácie?
Asi ano. 11:40.
11:40.
11:40 to bude asi.
Dobre. Čiže vtedy by mali ísť javy, dve prezentácie.
Jo.
Dobre. Takže vlastne potom sa pripojíme a...
Jo. My vás pro jistotu tady vás vyzvou a já vás i požádám o zapnutí mikrofonu, takže to uvidíte.
Dobre. Dobre, takže ide to.
Jo.
A potom sa
Dobře.
uvidíme,
Tak.
počujeme.
Jo. Tak děkuju a zatím nashledanou.
A ja, dovidenia.
Dobrý den, pane Krupa, můžeme jenom vyzkoušet, že se slyšíme vzájemně?
Takto. Haló, vyskúšam ich. Haló, počujeme sa? Účastníci. Video.
Slyšíme vás tady dobře.
Áno, dobre, takže ja som si to chcel len vyskúšať, som ešte prvýkrát s touto aplikáciou pracujem.
Jo,
tak počujeme sa dobre. Teraz idem iba separátne s vami, či ostatní ma počujú?
Slyší vás celý sál, takže to je...
Tak vás vítam. Tak.
My vás taky vítáme a tešíme sa na prednášku.
Dobre, ja sa teraz odhlasím, lebo mám ešte nejaké pracovné povinnosti a potom sa prihlásim dodatočne.
Dobře.
Ďakujem.
Tak naschle. No, my jsme museli přehodit, protože na nějaký jednání by to nestihlo.
Počkej, já to ještě myslím. Tady máš. Elane, tady to máš komplet. Ale nemáš tam teď tuhle změnu, jo? Takže začneme. Takže dobrý den, dámy a pánové.
Good morning, ladies and gentlemen. We're starting the second day of the Nuclear Days Conference. There are 3 sections on the program for today. The first section will be headed by Dr. Brumovsky, another doyen of the nuclear energy sector. This person was heavily involved in the delivery of the first reactors in Skoda. And then he spent a long period of his professional career at the Research Institute in Řeš. You have the floor and go ahead. Good morning, everybody. The first presentation will be from Jana Kalivodová from the Research Institute in Řeš. She'll be talking about materials for advanced nuclear power sector. We've got 20 minutes for each presentation, so please stick to your time slot so that we don't get delayed at the end of the day. Sorry, 10 minutes. Thank you very much. Thank you for inviting me and introducing me. It feels scary to speak right in front of this amazing array of experts, but I'll try anyway. I'm from the Research Institute in Řeš, and since my study time, I've been working in the field of materials for advanced nuclear power sector. I started to work particularly on the topic of materials for advanced nuclear power sector in 2014, having returned from a study tour to the Netherlands. And this is what my presentation is going to be about.
Takže je tak vlastně na pokračování, vlastně jasným pokračováním po generaci 2-3 lehkovodních.
This is obviously a continuation of the previous developments, meaning the generation 4 of the light water reactors. These reactors, as you know, produce more fuel than they consume, so they can provide power for hundreds of years. They also consume nuclear fuel, so they minimize the spent fuel waste. And they also work in higher temperature ranges, which means they are more efficient. But there's a downside to it. I'll be talking about the downside as well. And of course, they use passive safety systems based on physical laws, on the laws of physics, rather than the involvement of the human factor. That's why we talk about higher safety standards in these systems. What do the Generation 4 reactors actually need? And what are the challenges for us researchers? It's the materials. This is based on how the system evolves over time. The challenges we're facing are primarily consisting in the high levels of radiation, up to 100 dPa. And the individual systems have different coolants from the current systems, such as liquid metals, sodium, lead, bismuth, could be also helium and salts. And one can imagine just by that list that there's a host of issues that you need to handle. And the higher operating temperatures also up to 1000 degrees Celsius. That's what everybody can imagine. I just wanted to summarize what the current systems consist of. I'm sure these are known to you. It's either natrium cooled systems, also systems cooled by lead or gas. These are fast reactors. These are the GIV systems then. And I also decided to put here the systems that have been actually approved for the European Union, although France has decided to take a different route, and they are continuing in France together with Romania in developing a different system. Then we have the other systems and the countries in the Visegrad 4 countries. And the Allegra systems is a gas-cooled reactor, and the supercritical water, high-temperature thermal reactor, and other types. I've taken the liberty of listing this chart in order for you to see this summarizing table of the challenges that we're facing on the material front. I don't know if you can read this, but I'll give you a copy of my presentation later on, so don't worry. So what are the main challenges, the main issues that these advanced reactors are facing? Is the design in the first place. It needs to be for at least 60 or up to 60 years. Some of the large components are not exposed to high levels of radiation, but it's a long period of time. Then the next thing we need to take into account is the corrosive environment. So you're always handling issues of swelling, coverage, of corrosion, and compatibility of the various metals and materials used. Let me mention that a sodium-cooled fast reactor is the highest level, and probably the biggest challenge for us is the gas-cooled fast reactor known as Allegro. We're also active in the field of material studies and material research for water. There's a project called CC Smart, and for a molten salt reactor type of development. We are dealing with various issues that also the developers have been faced. High level alloys and molten salt is difficult in general. As I said, the challenges are on the material front. The materials need to be able to handle high temperatures and aggressive environment of the advanced coolants, and we are dealing with these issues with our foreign primarily European partners, and we try to optimize the current materials through optimizing or developing new processes. MATIS, GetMap, ChemMap, these are the areas or projects where we handle and try to handle these challenges. We need to make sure that this is scalable on an industrial scale. We need to make sure that this is a weldable material, high entropy alloy materials, etc. And last but not least, these new materials or the current materials, high temperature materials, need to be qualified so that the designers can use them for the real life construction.
So this is a summary of all types of materials that were listed in the strategic agenda of the GIV program for nuclear materials. So we all agreed what structural materials we have for what type of reactors and what materials should be taken forward into the future. So the main construction material for generation 4 reactors are the 316 materials, modified steels with 9% content of chromium 9 and 14. There are various coatings for the high temperature systems. We also put a lot of pressure on producing such alloys that will be self-coated, such as the alpha steels. So this is again a summary for the individual systems. So selected groups of materials for the systems. And just to get out of the tables and move forward, this is, for example, a material development for GFR VHTR, and we focused on corrosion, but also various selected mechanical properties. And we have to have a special device for that, either with static gas or a dynamic gas. For the dynamic gas, we need a bigger device with a GTL loop where we can achieve up to 900 degrees Celsius temperature. And of course, we monitor the condition of the gas, we analyze samples. And the whole work that my colleagues have done so far cannot be summarized on one slide, unfortunately. So I selected just two types of high temperature materials. First of all, materials for components, such as heat exchangers, pipes, and the whole secondary system. And then other materials for the coating of the high temperature cooled reactor. So we received certain samples of materials to analyze its oxidizing properties. So we looked at the material and the results were good. As for oxidizing, it was covering with a certain level, small level of oxides of silicium and of silica, and it was not a problem, nothing serious. We looked at the welds of the basic material, 800H, and there were bigger layers, but we cannot compare those materials because the first one is a structural material, the other one is used for coating. So there are different rules. So apart from testing materials, apart from testing the materials, we also look at what can be done with those materials. So this is an example of certain selected materials and what we do with it. For example, we developed a heat exchanger for high temperature helium. So it's a heat exchanger which works with helium on both sides, up to 850 degrees of Celsius. We used a number of techniques. We started with a small 3D print in Inconel, or the carbide of silica as a material. And we also used diffusion joining. And we cooperated with the Czech Technical University in Prague, and this is the result. So that's the heat exchanger, which we tested in a helium loop. And it was developed by a company called Ateco. And if such a system is ever going to be built, this is certainly usable. So it's a good example of how we use a specific material and how that material is further developed into an applied result. So this is another material or a group of materials for the coatings. So for the long time, we've been trying to improve various materials for coatings, the ODS alloys. With the ODS alloys, we can guarantee a long-term stability with high temperatures. We tried to work with nanoparticles, titanium or oxides, but there was a problem with manufacturing or welding or reproducing. So there's a long way to go. We'll have to keep developing and testing it further to get to any applied product, any applied material. So that's all on my side. Thank you for your attention. And if you have any questions, I'm ready to answer. Thank you for sticking to the time schedule. I should say that the developers in Rzesz are one of the founding members of European Research Association, and one of the parts or one of the committees focuses on developing materials for nuclear reactors of higher types, but also various technologies of storing nuclear waste underground and similar activities. I think we have time for one, maybe two questions. And a microphone needs to be used for us to hear. So how about the fast reactors in reality? Because if I remember properly, France is not operating its Phoenixes in the United States. They stopped developing these reactors so that the Soviet Union, Russia is not saying that they're developing plutonium. So do you have a strong support for your development, or do you have to do it piece by piece with small support? Okay, well, what would be a proper diplomatic answer to that? Well, we in Rzesz participate in the development of a high temperature gas-cooled reactor together with other Visegrad Group countries. And it's a long-term project. As you're saying, we're not receiving any massive financial support, so that is reflected in the development activities. We have some national projects for that. There's one European project for those activities. But of course, the activities are directly related to the amount of finances that we get. And the teams are not as big for the development to proceed really fast. And apart from that, it's one of the most demanding systems when it comes to safety. So we will have to build an experimental facility, experimental device to prove that it is safe. So we will have to continue validating in reality all the work that we do now just on paper. I don't know whether I answered your question. As you've said, the sodium system was suspended, its development was suspended, and France is not doing much when it comes to the fast reactors.
Thank you for the presentation.
Multi-physical modeling for advanced reactor systems. Is he here?
Yes, I'm here. I am just going to share my screen. Please let me know if you can see it. It is okay. Can you hear me? Hello, everyone. Can you hear me?
Yes.
Yes. Okay. So then I can start. So good morning, everyone. My name is Pablo Rubiolo. I'm a professor at Grenoble IMP. This is a university in south of France. And today I'm going to present our research activities in CNRS, so on the multi-physics modeling of advanced nuclear reactor systems. So I want to thank the organizer for inviting me for this presentation. So let me go on. So in the presentation, I will start discussing very quickly on the why in the industry and also in academia we are developing these multi-physics models, and then I will focus more in the activities in the laboratory, in our laboratory, and then giving 2 examples of application, and I will finish with some perspective on this. So why developing multi-physics model for nuclear reactors? As you know, and has been discussed in the previous presentation, there has been a general trend on the evolution of the reactor design for the last 80 years. We have had different generations. So today we are building the 3+ or the 3 generation reactors, and we are planning to build or starting the building of some of the 4 generation reactors. For methods and tools, there has been a similar evolution, although the driving force may not have been exactly the same. Actually, the increasing computing power and also the data that we got from the reactor fleets have helped to improve the modeling tools and the methodology that the industry has been using over the past 8 years. There is, of course, a coupling with the reactor design that have also been evolved. And the idea is that these new tools will help on the development of the generation 4 in particular. At the very beginning, the industry started using semi-empirical correlations and very simple models, 0D and 1D. By the 80s, we moved to standalone models, so just 1 physics and 2 or 3D modelization. And then from the year 2000, we start seeing more 3D models with full coupling between, for instance, neutronics and thermohydraulics. So these days we are looking more on to multi-physics model and multi-scale, where you have different models that will try to predict the result for different parts of the reactor. And the challenge is to go through the licensing process of those new tools and methods. So an example that is well known is the Virtual Environment for Reactor Application, VIRA, which is a platform that has been developed by the consortium CASTLE. In this case, academia and the industry just work together, developing a very large platform, digital platform that basically was using different codes developed by the industrial and also the national laboratories, and looking at different aspects of the reactor. And this virtual environment actually is able now to perform calculations that were not possible 10 years ago. Here's just an example of what can be done. For instance, in the PWR, we can look at steam line break accident, and there is no need to make the typical assumption that will be done for this type of accidents, like for instance, assuming that the power profile in the reactor is not going to change significantly. Here, basically, we have a full description of the core, and we can gather information, very detailed information on what's going on, for instance, in the fuel rods, what is happening in the peak of power, or if there is any oxidation on the client. So that's one example of a well-known multi-physics platform that is being used by the industry. Now, what are the advantages and drawbacks of this multi-physics based approach? the advantage is what I just presented before is that basically you can get from this type of model, you can get very high precision data, and you can generate best estimate of different parameters of interest. You can have access to local or micro-scale information, which is not usually possible even in experiment. For instance, if you use a CFD code, a computational fluid dynamic code, you can get the velocity any place in the field assembly, and this is something that is even difficult to measure in an experiment. So this type of tool allow obtaining better estimation of the design and safety margins, and this they have been used to improve either the fuel design or to increase, for instance, the reactor power, do a small power upgrades because of that better estimation of the safety margin. Now, what are the drawbacks and challenges of this model? Well, first of all, they have to include all the relevant phenomena, and that's not necessarily straightforward. It will depend on the complexity of the accident or the scenario that you're trying to study. They involve very high computational costs. That's not necessarily a problem, but if you need to perform many calculations, then it could be an issue. They need to be fed with a large amount of data, not always available. I mean, these are very detailed models, so you need to put all the data that is needed. On the other hand, the safety methodologies are not necessarily well suited for this multi-physics approach, because we are removing the conservatives, and then you need to develop novel methodologies, and very often you have to perform uncertainty propagation, so that makes more difficult the computational implementation of the tools. And then there are the licensing issues. So all these things are challenges that can be overcome, but also these are points that you need to consider whether or not to apply a multi-physics approach. So what are our activities here in Grenoble at CNRS, multi-physics and related to reactor physics? So first of all, we started working on this about 10 years ago, and the idea was to develop a multi-physics model, but also experiment to validate part of those models. We focus in applications where the implementation of the approach was realistic. So we look at systems that have usually simple geometries, which means that the mesh requirements are not excessive. So we can basically discretize the system using maybe 1 million or so of cells in the mesh, and we can focus more on the physics and on the phenomena. So the current application has been for the modeling of molten salt reactor. This is a reactor design that has been studied in detail by CNRS for about 20 years now. We also have looked at criticality accidents. We are currently looking also on the design of micromodular reactors and also for a reactor for nuclear space power. We are also working in liquid target for neutron production. So, and a key point here is the comparison between the model and the experiment that we can perform. So today I will very quickly talk about molten salt reactors and criticality accident as example of application of this type of approach. Now, as I say, the developing multi-physics model requires also validation of the phenomena, the way you are modeling the phenomena. So, and that you have to be sure that you are capturing all the key and relevant phenomena. So you have to perform a paired, so phenomena identification ranking table, where you have to ensure that you're not forgetting anything that is important. Once you have done that, then the idea is we develop the numerical model, and we also try to develop experiments that can help to assess on the precision of the model. So in our case, we have been focused mostly on turbulence, phase change, thermal radiation, porous medium, and also the effect of internal heat sources. And the reason was that we were mostly looking at the case of molten salt coolants. And then, of course, at the end, the goal is to compare the model prediction with experimental data. So let's look at the example of the molten salt fast reactor. This is a reactor that is being studied here in Grenoble, and now it is the object of an European project, Safer. So this is a reactor that is using a molten salt as a fuel carrier and also coolant. It's a fast reactor, so it has a cavity. This is just a sketch. This is not the actual geometry of design. So you have a core cavity where you reach criticality, then the molten fuel salt will just flow through the pumps and then heat exchanger. And in the reference design, we're using a thorium fuel cycle. There is no moderator, of course. There are no control rods because the reactivity control is done by temperature based on the heat exchange on the heat exchanger. There are 3 loops. There is the fuel cell loop, and then there are other 2 loops. And the operating conditions are quite demanding, so we are working at high temperature, but low pressure and recirculation times that are about 4 seconds. So this system is very different from a PWR. As I say, there is we have a liquid fuel. There are no control rods. And more important, if I go back, one of the control system is the draining of the fuel in the cavity. So if there is an issue, we can drain the fuel through the draining salt draining system to a draining tank, where we will, because of the geometry, we will be able to cool down the fuel salt and also ensure that we are subcritical. So this fuel draining system is very important. It has been the object of some studies that I will present. So the multiphysics model that we use in CNRS is based on the coupling between 2 codes. One is a CFD code, the name is OpenFOAM. The other one is Serpent code, which is a Monte Carlo. Basically, it has 3 components: the neutronics, the thermohydraulics, and thermomechanics. And for this specific case, there was a PhD collaboration that was focused on the development of the neutronics model that I'm not going to describe right now, but just giving an idea. And then the thermomechanics model, because the salt will can go melting or solidification. And then, of course, thermohydraulics, because we are in turbulent regime. So the example of application for this reactor was a transient of the draining of the molten salt during a station blackout. So we assume that, for instance, we lost the power, and then we have to drain as fast as we can the fuel, so we don't reach a too high temperature that can damage the extractor. So we have the cold plugs. These are like a safety device that will melt if we lost the power, and then the salt will just go down through the draining system. So if you want to model that transient, then you need to have quite complex physical models that are listed here. And this is possible only if you have a multi-physics model. And here I'm showing for instance, the geometry that was used for the study. And you can see the draining of the molten fuel salt. The color represents the temperature, and what we were checking there was that we're not exceeding the maximum temperature of the extractors. So this is type of study that you cannot do with typical or a classic standard code. So we had also to validate some of the models that we were using, and in the laboratory we built a facility. The name is SWAT, where we can perform experiment with FlyNet, which is a molten salt. And there we study, for instance, the solidification model. We compare the experiment with the model predictions. And we also study heat transfer and the working of the cold plug, which is the device, the safety device that will allow for the draining of the salt in the reactor. And now, based on the experiments, we came with a cold plug design that was used in the European project. So that was a case of application of a multi-physics model for the case of generation for reactor. Let me give you another example. We use the same model with some modification, but now to study criticality accidents. So actually there are very common points between the molten salt reactor and some of the criticality accidents, because we can be working with homogeneous system, which is similar to what we have in the core of a molten salt reactor. So a criticality accident is an involuntary and uncontrolled fission chain reaction. And this work was done in the framework of a collaboration with the safety authority in France. And the idea was to develop, to use this multiphysics model to study all possible criticality accidents. So we performed a survey of different type of accidents, and we came with the three that you can see there. So we can have the transient or experiments related to criticality accident in solid media. We can have accident in liquid media, or we can have accident in heterogeneous media like spent fluid pools. So the idea was to prove that the model could be used in any of these systems that are characterized by very different time and space scales. In particular, the work was focused on the neutronic methods, and we look in function of the different parameters like the direction, the angle of the neutrons, the time, and the energy. We look at different methods that could be used for the modeling, and we choose a deterministic method that is which is here in blue. So it's an SPN method that is quite standard in the industry. And then we look at a different method that was based on a Monte Carlo quasi-static approach. Basically, we use a Monte Carlo method that is very precise, but very heavy also to implement. And we implement those two models in the previous multiphysics tool in order to study these criticality accidents. We also have to perform some modeling on the stress analysis because of systems like solid medium. And then we study different cases. And here, for instance, I'm giving you the example of the Godiva experiment. This is a very small critical facility that use high enriched uranium. There is a sphere that about 9 centimeters, so very small. So if you want to use a diffusion approach, it won't work. You need to use a Monte Carlo approach usually for this. And the idea is that in the experiment, you will induce a prompt burst that will cause a very quick increase of the power that you can see here. The scale is in microseconds, and the power is in gigawatts. So the power is quite impressed, but the duration is so short that the temperature increase of the sphere is very little. Now, the transient is driven by the thermal expansion of the sphere because there is no Doppler effect. And what we show here are the prediction of the model for the reactivity variation and how the system is go to a control situation. And what we found was that we were able to predict with a very good accuracy using these multiphysics tools, coupling between the thermomechanics and the neutronic modeling. So to finish my presentation, let me give you some perspective. So right now, the idea is that this multiphysics approach will be, we will see them more and more often in the studies performed by the nuclear industry. There are novel applications, and this approach will be very useful for the design of the current nuclear power plants, advanced reactor design, but also for novel fuel like the accident tolerant fuels. But in any case, you only have to ask you whether the multiphysics tool is really needed, because in some cases, as I explained earlier, it's not the more efficient approach. Now, an important point is that it is necessary to have an international collaborative framework for developing this type of tool. And an example of that is the open source nuclear code for reactor analysis initiative that is being supported by the IAEA, and whose main goal is to promote the development and application of open source multiphysics simulation tools in support of research and education. I didn't mention that, but one of the goals of our activity is also to keep a high level training in the university. So this initiative of IAEA can be joined by anyone, and the reference is just given here. So, and that's finished my presentation. Thank you very much.
Teď se trošku vrátíme do současnosti a do reality, a další dvě prezentace budou ze školy jaderné strojírenství. První bude od Ladislava Soukupa, jaderné upravárenství hlavních komponent jaderných elektráren.
Dobrý den, já
Já jsem si připravil takovou malou ochutnávku toho.
Hello, everybody. I've got a little tasting there of what we do. You seem to have disconnected my presentation. All right, so this is a little tasting of what we do, what we're good at. Although this might not be the thing that is presented in the media and that is generally known, although this is our strength. That is the repair methods for the main components of nuclear power plants in the VVER system in Czech conditions. And without the wherewithal to do this, we would not be able to operate nuclear power plants. And that's something obviously that needs to be technologically advanced so that it is in line with the requirements for the given power plant. And there's a history to our knowledge base. All right, I'll turn around like this and speak to the mic. Why are we good at this? Is because we have a long history, a long tradition that dates back to the 1960s. And for instance, welding is one of the pillars in the A1 type reactor. This is a long history, and that brought us to where we are now. This is just an illustration of the Czechoslovak developed reactor. That's the wonderful history of our nuclear power sector. So this is a comparison of the former, the original one, A1, called A1, and the today's version of it. So these were the foundations of our knowledge and competences. Of course, a nuclear power plant is a very complex network of systems, structures, and components. So a detailed knowledge of every single system involved is the prerequisite for you to be able to repair in a professional manner all these components. And there are two main things to take into account: corrosion and the degradation of materials. So these are the two main challenges that we face, and that essentially are the reason for our necessity to be able to repair materials and major components. There is a cycle typically to a nuclear power plant, and we are talking about the last but one, that is before decommissioning, of course, and then there are set rules for all this, and we need to comply with the designer's requirements and the requirements for repairs. And based on our own knowledge base and knowledge of materials and our competencies, we're able to handle the repair projects. Major repairs and overhauls started off in the 1980s. Few people know today that we were actually repairing two vessels in the Jaslovské Bohunice power plant. One was operated, they were sub-weld cracks that we corrected and repaired. And it was a pretty interesting type of repair, if you think of it in terms of welding. We needed to develop a system to support the structural strength of the welds. Two different materials, several different materials. The first material is, the base material, is sensitive to austenitic structures. So you need a very special processes in place and procedures in place in order to be able to weld these sorts of materials. So that's just a little tasting of the historical developments that brought us to where we are now. And we call it nuclear repair projects. And as I said, welding is one of the key technologies. So there's a very deep and broad knowledge base that we've developed over the years. You need to be very sure about what you're doing in terms of the materials and the procedures in welding. I think without the historical experience, I think we would be very hard pressed to handle things like repairing by welding, piping, or heat exchange piping, and etc., etc. This is just a brief overview of the main milestones in the last decade. And you realize that this makes you realize that repairs are an everyday thing. With some of the nuclear power plants in Dukovany, it's more often, it's less often for the Temelín nuclear power plant, and there were no major repairs. I will leave you a copy of this presentation, so I'll just skip through this and zip through this quickly. The main prerequisites are obviously the licensing. Some people are fond of the idea of harmonizing the repair procedures with the European standards. I don't think that is a good idea. I would actually argue that is a nonsense, because it's based on the existing design and the design standards. And it is now being changed, for instance, in Russia, to the latest standards. But these are mutually compatible. Very importantly, it's like the ASME code is one aspect, but if you actually repair an older Westinghouse nuclear power plant, you need to actually go back and refer to the ASME standard of that particular historical period. Some people, as I said, are fond of the idea that we should harmonize these standards with the European standards. Not that easy. It would be a superstructure to what we are doing, I would say. Now, importantly, you get to do some very serious repairs, very major repairs of serious problems. And this is a heterogeneous weld of connecting the primary pipe to the steam generator. On the left bottom side, left bottom picture, you see the partially cut flange and or neck actually, and there are cracks that we followed, that we actually discovered by a capillary check. And you need to cut out a whole section and then repair in and weld in a new section, thereby repairing the whole pipe. Then you see the macrostructure of the new weld. You can see it's a huge weld, 70 millimeter thickness of the wall, and you can see a very thick bead there of the weld towards the steel. And this is a steam generator. We're talking about the pipe flange and pipe system to exchange heat or to transfer heat from the primary system. So the main problem is the weld is actually shrinking. That's up to 15 millimeters with this side of the size, sorry, of the weld. So we had to minimize the shrinking. It was a controlled deformation using screws, and we were literally controlling using huge screwing systems and fixtures to reduce the shrinking. And you can see on the right the simulation or modeling of the shrinking process. That's a standard thing we do today.
Another unique technology of a hypothetical repairs of weld cracks in a high pressure reactor. You can see a robot using a TIG method, working on a wall that represents a reactor wall. It's a unique technology which has not been deployed yet anywhere in the world, so we keep pace with the rest of the world. It's a multi-layer weld, and every layer had to be scanned with a laser. You can see the laser. And we used software calculations and then continued with welding the second layer. By the way, the university that you are at this moment developed the software for that. And the welding material, Iconel 52, that's a material that we use in Western type reactors. Another interesting repair, not so unique, but interesting, is a local manipulation with water in case of expected cracks. So you have to take out the water, and it's a huge volume of material to be able to weld the crack. So the material needs to be pre-welded, then there must be some thermal processing and additional welding to be done. So technologically, it's a complex situation. Luckily, we haven't had any crack of that type yet, so we didn't have to do this kind of a repair. It's a problem in developing various technologies for repairs. We develop procedures that theoretically may be needed, and we're waiting for the situation to occur, and it does or it doesn't. It looks like our steam generators are of a high quality because we do not have a need for these types of repairs, but some technicians know that there could be a problem like this. So when we did a local repair of a small part of the weld, let's say in 1 year, there was a problem in another part of the weld because the first repair changes the distribution of tensions and so on. So this is a repair in Dukovany. That's a huge weld, the biggest one that we've done. And it's done on a 24-hour-a-day regime on 3 shifts, and the repair takes 21 days. So from the identification of the defect to cutting it out to using a manual technology of a coated electrode. And as I said, it takes 21 days. Of course, we can imagine that an automation and orbital welding systems could be used. So this repair, luckily, again, didn't have to be put in practice. Hopefully, we will not have to use that in the future because we would have to experiment with that. It would be a remote, robot-controlled repair, and we only tested the welding technology and the materials. This has not been done in reality either, luckily. This is another unique device. It's an orbital welding device to replace parts of the steam generator collectors in Dukovany. At the upper part, you can see the threading and the lid of the primary cycle, and there's potential of corrosion. If there is any corrosion, it needs to be repaired. The whole part is cut out and a new part is welded onto it. What is specific is that the burner is on the inner side, so we're welding from the outside towards the inside, towards the axis. So we're using steel of 316L type. Another interesting repair or a technology is a production of various interim and transitional parts. This is a welding of a heterogeneous weld to the carbon part. Then we add the double part and we weld it on. It's an automated system, a mechanical welding using a TIC method. On the right-hand side, it's a specific application. It's a piping in the steam generator, which is a lead piping for the water, which then changes into steam in the steam generator. The radius is 370 something millimeters. I don't remember the exact number. So this is the newest activity that we've been developing, or we've been taking part in for some 2 years. It's a manufacturing and welding of a new pipe onto the main piping. Because of corrosion, we need to replace the lead-in pipe. There's a homogeneous weld, then a transitional heterogeneous joint, and austenitic cone. And you can see a model 1-to-1 with one segment of the primary pipe, and you can see the qualified joint and the burner that was used for the welding. These are some details from the developing of the technology for the repair of that entrance. You can see the front weld onto the primary segment. These are real segments and original materials, and we have to create a transitional joint using the same automated tool with an anti-corrosion burner. We do the welding, and you can see the device which is fixed onto the testing rings, HTC. It's a unique technology. Basically, we do not have any other device in our country that would be capable of using that method of welding. The same technology was being developed in the 80s for the welding used for VVR reactors in Škoda. But back in the 80s, we haven't had such sophisticated CNC-controlled welding heads that would manage this. Today, we could do it. So this is an example of a material study. So on the right-hand side, you can see that complex structure of heterogeneous welding and a colored map of that. So the color-coded map shows the whole system and how it changes. So that was just for you to taste a little bit of what we do in Škoda, what we are capable of doing. And I can tell you that this is a highly demanding area of activities. You have to have many experts, material specialists, technologists, computer experts participating in this. So it's not one person involved in such activities. You may have one person managing the whole project, but he must have at his or her disposal all the experts that have that specific know-how. So we're trying to keep up with the rest of the world, and the examples that I showed to you prove that we do keep pace with all the developmental trends in the world. So, for example, in recent years, we were forced to apply the fully automated robot-controlled welding. And you could see it in one of those examples that I presented to you. So that's all on my behalf when it comes to new technologies in repair projects.
Thank you for the presentation. We'll leave the Q&A session towards the end of this part. Our next presentation will be again from the same company, and Ladislav Benir will be talking about the new welding technologies for nuclear power sector. Good morning, everybody. I'm glad I can share with you the latest developments in our company. Unlike Tomáš, who spoke before me, who works on the servicing side of things, I represent the manufacturing side of things. Whatever I will be talking about, you can actually see in 3D in a place that is about 15-minute walk from here, down at the Skoda premises in the reactor hall. Very interesting stuff happening there. And I will pick up where I've left off the last time, if you don't mind. Now it's up and running. Good. This is known as the reactor hall of the Skoda JS company. And we are back in business, so to speak. Those of you who don't know the history of our company, you're very cordially invited to see that place. This is one of our products that we shipped about 2 years ago. This was the first container for spent fuel for the Temelín nuclear power plant. Quite an interesting bit of equipment in terms of welding. There was a circumferential weld with the wall thickness being 450 millimeters. I've shown this as well. I did it last year. This is the basket, shall we say, for the 1000 reactor. This is austenitic steel with the 1.7% content of boron. Very unique. Another unique piece of equipment, although old now, is another container for the Dukovany nuclear power plant. We shipped this one a couple of weeks ago. After 2 years of welding production, we were able to manufacture this container, now successfully shipped, and we got to weld an even larger circumferential, and even thicker wall, actually, 465 millimeters. I think this is unique. This is probably number one all over the world. So far, I haven't heard anything of any project that we're actually surpassing this parameter. I have prepared for this year's Nuclear Days also a presentation about the chemical production. We are currently working on a chemical reactor. It's incredibly interesting. But I will first speak about the nuclear power sector. We landed 2 contracts for the in-containment components for Hinkley Point, and I just put the map in the presentation so that people know where Hinkley Point is. We've already done these core barrels for the EPR, and this was one for Olkiluoto 3 for that power plant. Now the photographs, these very photographs of the core barrel are about 10 years old, and I don't think this is operated as yet up in that plant, but that's not our problem. This was a successful project and we delivered on time. Last year, I touched upon one thing. We weld this in the reactor hall. It's the austenitic steel, 19% boron and chromium. nickel and chromium, and we have an additional material. And unlike the traditional materials where you need to preheat, we have this interpass temperature of 100 degrees Celsius prescribed, so we need to stick to that. Even years ago, we were faced with the necessity to back up and provide arguments for the correctness of our solution to the well. So this is the system we use, how we put together the wells. The first step is that you use an electrode weld, then you fill it up with the bead, then you need to machine this, and from the other side you do the same thing, using the molten material. It's an old traditional procedure of welding that our ancestors used for the 1000 reactor, and we kind of revived it and tweaked it to the modern shape. These are the photographs that I showed last year. So this is where I left off, so I'd like to pick up here. We are using essentially a fixture that is actually designed for something completely different. And this positioning device has a load capacity of 250 tons. That's very helpful for this kind of thing. And the welders work about 8 meters above ground. And this is the view from the ground. So this is what you see if you walk underneath. And this is from the portal crane. This is a view from the portal crane. Our colleagues are working hard, facing tough safety, health and safety regulations, and are checking on the bead, the welding bead, to be correctly produced. If you wanted to see this in real life, you can do it. Just visit us. It's a 15-minute walk from here. Why do we actually use this positioning device? It was something that was designed for the bottoms of the pressurized vessels, and that's exactly what this was actually intended for. But we also use it for positioning huge pieces of components for welding. It cost a lot to develop and make it, so I think it's good we can put it to use again. And frankly, I was telling my colleague the other day, I admire the courage of the people who designed this and who manufacture this. It's a huge thing. It's a huge structure, and it's working perfectly. The only difference between that photograph and the reality is the color of the coating. This one is older, as you can see. That was back from the Dukovany and Temelin period. Temperature treating is, thermal treating is obviously another part of our work. We've learned how to work with preheating and how to thermally treat the material. We need to use local annealing for that shaft, and the local annealing is done at 400 degrees Celsius. It's some kind of stabilization annealing in order to remove inner tensions and also to stick to the dimensions, to keep the dimensions of the whole piece. And this is prescribed by the project. And we use the heat masters and heat generators. There are 14 of them, which is a record number. And there's a local Pilsen-based company who are really doing a great job, arc heating, and they are doing great calculations in terms of the heat necessary for the annealing procedure to take place. This is what it looks like in practice. So you need obviously a full-fledged, detailed project for every single type of operation of this sort. So in terms of health and safety, you need to be able to put in the scaffolding, And then, having built the scaffolding, you can start doing your job. And these are the heat sources of heat, heaters. There are 14 of them, and some of them can be seen on this photograph.
So this is an image of welding of the upper part of the shaft, and the final outer weld has not been done yet. We will do it. So this is work in progress of the inner parts. This is the situation as we speak. So we were doing the annealing, and you can see that it changes color when we anneal it to 200 degrees of Celsius. It turns gold. So this is history. This is an ammonia reactor that we manufactured some 15 years ago. So this is the closing weld, and we are close to this closing weld, and that's where my presentation will end. We've done both halves, and we're starting to weld the two halves together. So that was history, and now back to the present. We're doing it for Záluží u Litvínov, for a company called ROS, so that's the customer. And we have to do a lot of preheating, which is interesting. For those of you that are active in this field, you would know that a temperature around 300 degrees of Celsius is quite high. Our limit is 200 to 320 degrees, and we try to keep it above 300. So for the welders, it's a tough job to move in such an environment. Of course, we try to apply insulation, but it's not always possible because there must be some entrance road to the weld. So this is an image of the forging, which was in the reactor last year, I believe. So that's the forging from the 15 millimeter steel that the reactor is put in together from. So these are the heating circles, and I must say that we stopped using induction heating, which is a pity, but because of the development in our company, when we had a pause in large-scale welding, we somehow let the induction heating die, so to say. So we're back to a situation when we have these resistance welders or heaters rather. So this is what it looks like. And you can see that there's a lot of cabling. You have to keep it in order, know what cable leads where. And the temperature is regulated on the product thanks to a heat sensor. So this is again interesting. Where I'm pointing on that slide, that is a narrow entrance, a narrow head, and we thought that we wouldn't use it any longer. That's a head that we used to weld all the complex settings. But that was in the past. We have a new head. But because we needed to increase the volume of work that we do, we have to be able to weld simultaneously the containers or the barrels and the reactor. So we had to take this old head out again from the storage and start using it again. So this is the place where we put the individual circles together and welded them onto each other. This is the head of the reactor. And again, you can see that it's really complicated to properly insulate it and heat it. And it takes time. It may take 2 days to reach 300 degrees of Celsius, and then we have to maintain the temperature on that level. So these are operators working on the piece, and this is the last action photo, the operator is trying to monitor the process. And of course, he wears all sorts of protection fittings. He also has his own oxygen source because he's working in an environment which is really hot. The problem is that the reactor does not fit in the furnace as one piece. So we have to do the annealing in two parts. And that's what we're working on right now. We have to do the closing weld while preheating, then continue with the heating, and then do a resistance annealing, resistance induction annealing. So if next year I am here with you at the conference, I will present the final works to you. So at this moment, we did the necessary machining. So that's this photo. Then we put it on the horizontal positioners. And this is a photo from yesterday. That's a very present, very topical image of what we're doing at this moment, of joints joining the two pieces together. So we're using external joints, and it is insulated inside. Then we let the welders inside to weld it. Then we remove the joints, and we will continue welding from the outside. That's a process that we've been doing for years. So the vessel on the surface will have 300 degrees of Celsius. And of course, we have to let the people in with the electrodes for welding. So it's quite a difficult piece of cake. They will be welding in an environment which is around 70 degrees of Celsius. That's a bit more than in Egypt. So they will get quite hot inside there. And I found something which is really interesting, a piece of product that we believe is something for the future, the repositories of fuel. We developed a model to show that that's going to work for the deep repositories. So the repository administrator will use that model to present how we're going to store fuel in deep repositories in the future. So that was just a piece of interesting information. And last but not least, thanks to the team, because we're not doing our work in isolation. And this is a team that took part at all the work I presented to you. So that's the end of my presentation. Thank you. Thank you for interesting pictures that brought us back to the past. So now again, a change of the presenter. Instead of Mathieu, we're going to have Martin Valňat from Czech Institute, who will present the Energy Well project.
Good morning, ladies and gentlemen. There are ladies, so it is ladies and gentlemen. Yes, sorry about the mic. Thank you. My name is Martin Vaňka. I'm from the Research Institute in Řeš. And I'd like to talk to you about our concept of a small modular reactor. And it's known as Energy Well. So that's the title of my presentation. The clicker seems to work. So let me just say who we are. The Research Center or Research Institute in Řeš is something that you probably know, but in case you don't, we were founded in 2002 a subsidiary of the Nuclear Research Institute. So the UJV is mother company, so to speak. And our main business, the main focus of what we do is research and development, primarily for the nuclear power sector. But it's not the only thing we do. We also have a department that deals with nitrogen technologies, and we are also involved in development and research in the fields like water purification, for instance, or wastewater treatment, etc., etc. As most of you know, we have two research reactors or two school reactors on the premises in Řež. I represent the department responsible for large technology projects. So, as the name suggests, we are responsible for high scale or large scale projects. For instance, projects like the hot chambers for the French based nuclear projects. The Czech Republic is a partner, and the UJV is responsible for the hot chambers in terms of the design and supervising the delivery. Another project that I will just briefly mention is the ESS project, and we are responsible for the helium cooling circuit. The picture on the left, the bottom, shows you how beautiful can the landscape be around the research center. The next picture shows the mixture of 10 tons of piping and all the rest of it, with shielding and sealing functions as all the rest of it. Sorry, that's on the right. And the reactor that we fondly label Helča was on the picture in the center. But that's not the topic of my presentation. In 2017, somebody got the bright idea that we should have a vision, that a Czech company should develop and design a small modular reactor. A couple of enthusiasts decided to grab the bull by the horns, and this is a picture from 2017. This was literally a vision. You can see in a moment, you will see in a moment, that it's changed a lot since then. But in the meantime, we were able to secure a patent for the design and the concept of what is known as Energy Well, the small modular reactor. That happened in 2020. And our project called Energy Well is registered and published in the booklet of the International Atomic Energy Agency, IAEA. I think there are 70 plus other designers listed in that publication who work in the field of small and micro modular reactors. Ours is small, in the small category. We are working with chloride salts, and my presentation, just to let you know, is not very detailed when it comes to the technical specifications. Of course, I can try to answer your technical questions as well, but I'd rather give you an explanation and some illustration of what we do, what the concept is about, what are the advantages and disadvantages of this sort of design, what remains to be done, and what we've done so far. So Energy Well is in the category of micro SMR, small modular reactors with 20 megawatt thermal, roughly 8.5 megawatt electrical output. My colleague Marek Kruščák is fond of saying it will provide energy to a town with 16,000 inhabitants, and he likes Dvůr Králové, which is exactly the number of people who live in that town. So that is just to give you an idea what we can provide energy for, how many people or households. So what is the energy well reactor? It's used for producing heat or electricity. It should be said and/or electricity. It can be both. With applications ranging from supporting the energy consumption requirements for the towns of the size of Dvůr Králové. And it can also support the energy requirement or cover the demand for electricity in certain companies. For instance, I can imagine the Skoda works having their own source of energy using this micro reactor. Also, there are applications that you can think of with very remote locations where you don't have to have operators on site. It can be a temporary solution and can be all sorts of things. So it's pretty universal when you think of the applications. We have a shielding container. This is all inside the shielding container that is also used for transport. I'll show you later. The secondary and tertiary circuit, at least we imagine so, would be located in the traditional ISO-compatible containers that are used on large ships. The advantage of this arrangement is that you simply need 3 containers, literally on wheels. You bring the stuff to a site and you can put it up. It's very easy to install, maintain, and it's also very easy to decommission. All the preparatory and maintenance work will be essentially done in the manufacturer's production hall. And I really like this picture of the truck, so I'm kind of fond of showing this. Imagine this as the factory, the centralized processing factory that's up on the bottom, the top left. Then you put the transport container onto a truck, and the container is not just a container, it's a full-fledged primary zone in containment, really. You put it onto a truck, you ship it off to the site, you connect it to the grid, you literally screw on the flanges, and there you go. You're ready to run the device. After 7 years, which is the prescribed period for maintenance, the primary circuit is removed and brought over to the factory. This is a detailed life cycle picture of the unit.
So manufacturing in one central manufacturing site, then transportation, and 7 years of operation, then reactor exchange, and again you can start another 7-year cycle. During the reactor exchange, and I'm going to show it to you on the next slide, this is a layout, and there are 2 pits in our concept, and one of them is always actively connected, the other one is left out for 3 years to cool. So the cool down period is 3 years. The calculations talked about a year plus, a year something, but we have the cooling period set to 3 years. Then it is transported back to the hall and replaced with the new one. So this is a process flow diagram. What is most important is that the primary and secondary circuits contain fluoride salts. The tertiary circuit uses supercritical CO2. So the overall layout as we see it, what it should look like. The overall build-up area is not large. It's 20 meters on 10 meters, let's say 200 square meters. And as I said, we always use 2 pits. One of the pits is actively connected. The other one is in the cool down period. That is the 3-year period for it to cool down, so that we're able to transport it back to our hall. So we're thinking about developing a modular layout when it comes to the area above the pits. I can imagine that conditions in Alaska and conditions in the Sahara Desert can differ quite a lot. So you will need different equipment. So that's why it should be modular. I will not go into technical details, but this is the primary circuit as we designed it. So you can see the transport container containing the reactor vessel. So the vessel is in the container during transport and during operations. There are flyby molten salts in it. The layout of the secondary and tertiary circuits. And again, I will not go into technical details. As for nuclear fuel for our energy well SMR, nuclear fuel that we opted for is the American TRISO. And I always imagine it as that one ball being of a size of a poppy seed. So it's a very small ball of uranium pressed. There are a number of layers of carbide. So these are small pellets, pressed out pellets, and this is the slide which describes the current activities on the design. So it is our objective to complete the design by 2025. So our activities are focusing on that year, because on that year we should complete our design work and we should be ready to build a mock-up non-active unit. Of course, throughout the period, we're doing various safety calculations, we're verifying available system codes. We're also discussing our concept with potential users. We're trying to identify selected locations for our reactor to be built in the future. It's a start, but it's an important start. So as I said, we're focusing on building a mock-up facility, a testing facility, and an important thing that is in front of us, it has actually started, but the main part of it is in front of us. We'll have to discuss it with the regulator in the Czech Republic. So we'll have to discuss the current legislation in our country when it comes to small modular reactors. And these discussions will be very long. It will be a tough struggle. So not to be overly positive, we have many difficulties and points of clarifications to be made. So as I said in the beginning, the transport container is not just meant for transport. So we have to complete the design of the transport container. We have to put everything on paper. We have to think about various tests to be done before transport, do some simulations and measurements before and after transport to guarantee safety and compliance with all regulations. So transporting the vessel with the container altogether, it should weigh some 190 tons. So that's one of the challenges. Then melting of the primary salts in the vessel. That's still not clear. So at this moment, we're conducting some simulations to see whether it will be possible to transport the container and the whole primary circuit with the salts inside. So we're having detailed discussions which way to go, and we'll have to discuss it with the regulator, of course, later on. And because we're trying to fit everything in a small space, that is the transport container, it's a big challenge for us technicians because we have to come up with a layout of the individual parts to fit it in, because we really have to work with limited space. So this is what I've already touched on, our future outlook, what we want to do up to 2025, because by 2025, we want to finish the basic design. By 2030, we would like to have the non-nuclear mock-up, and by 2040, we would like to have an operational unit, a commercial unit up and running. So since the very beginning, we have approached the project as Czech know-how and Czech ownership. So we have had discussions with various suppliers in the nuclear field, and most of the key components, and that is our target, should be supplied by Czech manufacturers. So we would like to maintain our Czech nuclear know-how and continue developing it. So we have had discussions with Škoda JS when it comes to the transport container, and also Škoda JS, Miko, and Ateco are foreseen to be the suppliers for main components, and then ZAT, Dell as data partners, then division of the Nuclear Development Institute called Energo Project could be the main engineering company. Then Sigma as a supplier for the pumps and valves and so forth. So the know-how in the Czech Republic is huge, and it's our objective to use it and keep this project for the Czech industry and Czech people. And just for your interest, This is our model. The scale is 1 to 20, and it will be exhibited at the Expo 2020. It was exhibited in the Expo 2020 in Dubai. So it is the stainless steel model, even though the containment is plastic, but the components are from stainless steel. So if you visit Dubai, you can see this model. And my colleague has just told me that the previous model that we had made, the previous version of Energy Well is exhibited here at the university. So that's all on my side. I probably have forgotten to say a lot, but well, time is up.
Thank you. Again, if there are any questions, we'll leave it to the Q&A session at the end of this block. And the last presentation is by Josef Belac, the field coverage for VVER reactors.
Dobrý den, pane předsedo.
Hello, everybody. Thank you for giving me the floor, Chair. I hope you can hear me. Yes, we can hear you. All right, so I will try to share my screen with you. Let me talk about our contribution to what is known as accident-tolerant fuel for nuclear power plants. That's something our company has been involved in for several years. Let me start by saying how we got to develop this kind of thing and how our company is involved in Czech and international activities in this field. And then I'd like to share with you the conclusions and the outcomes of our development effort. The outcome is actually a qualified technology and qualification of the manufacturing of various types of accident-tolerant fuel cladding for chromium-coated systems for the various applications. So the issues of accident-tolerant fuels essentially arose as something that happened in practice, and we had to respond to it as a result of in consequence of the Fukushima nuclear power plant accident. And right after that accident, there were all sorts of efforts everywhere to improve and enhance the tolerance levels, the withholding capabilities of the fuel rods. And of course, the purpose of this whole effort is to make the fuels generally more tolerant for the operational range of situations, but also, in particular, for any accidents. In the United States and elsewhere, there have been a lot of initiatives and various efforts made in essentially two main directions. One is trying to improve the already historically proven and very well working fuel of combination fuel based on UO2, and zirconium alloy fuel system. Various alloys are used. And as the Fukushima Daiichi and the other accident showed, one of the main problems that this concept is faced with is that if there is heavy accident, there is exothermic reaction and production of nitrogen and very quick degradation of the fuel in this kind of environment. So in order to improve the behavior of the fuel in heavy accidents, various research activities have been started in order to improve the tolerance of the current existing fuels and power plants, as well as the future ones. We're talking about heavy accidents, serious accidents. In the past 10 years, globally speaking, there has been a lot of screening efforts, international seminars, conferences, and various activities held in the US, in Japan, and elsewhere. We seem to have lost connection, sorry.
Tak. Doufám, že teď to funguje.
All right, I hope I'm back online with you. Yes, we can hear you. Please go ahead.
Takže já si dovolím pokračovat.
Okay, sorry about the mishap. I'll try to continue. On the concept of the accident-tolerant fuels, the developmental concept can be divided into three groups. The first one is focusing on the fuel itself, and the second one on the cladding of the fuel, and the third one on the components that don't contain directly fuel, for instance, the control tools, various absorbers, and various auxiliary components of the passive type. Now, there are various levels of industrial maturity, shall we say, that can be seen in this development effort. We've come closer to the industrial application in the concept that is based on the traditional type of the zirconium cladding and the UO2 fuel. But there are other concepts that can be used. On the right side of this picture, you can see various cladding materials. It can be coating, zirconium alloy types of materials, or it can be improved, enhanced zirconium alloys for the cladding itself. And then also, in the past, the previously tested concepts are being revisited, such as silicon carbide and ceramic coatings and advanced steel coatings, or perhaps refractory-based or refractory metal-based coatings, such as molybdenum and etc. With the advanced materials, perhaps with the exception of silicon carbide, we see a negative impact on the neutron transport, and thereby on the economy of the device, which is definitely not good. Coming to the ceramic and silicon carbide materials, it's difficult to make these materials seal-proof, and sealing the fuel rods is difficult then. Talking about the fuels themselves, the development again takes various paths, various directions. One of them is advanced ceramic fuels that is usually enhanced by components that increase the thermal properties and conductivity of the fuel, and that is to make sure that if there is an accident, the fuel can be easily or cooled in an easier way. Other developments have included enclosed fuels or perhaps higher density of uranium for the fuel itself. I'm not going to talk for too long about the individual components. It's usually either the cladding of the fuel cells or the control mechanisms, control components. If they are made of zirconium alloys, then the threat of exothermal reaction obviously includes also these components. And in that case, it's absolutely justified to think about the properties that should be improved and trying to find ways to improve them in serious heavy accidents.
So now I have to go back. Our company, Albel, has intensely researched in the past 4 years the various cladding concepts. We've conducted a large screening, an extensive screening with a comprehensive testing matrix, and we continued researching various alternatives. Primarily, we looked at the deposition process using magnetron sputtering. The basic material is that standard alloy F110, which is used in the VVR types of reactors. We tried out various types of coatings, but basically all of them, with the exception of the last one, were on the basis of chromium. We also tried titanium-based coating, and when we look at the tests and their outcomes, we selected our final concepts. As for the testing and the results, we had to conclude that the new coating materials certainly have better features in the standard operating conditions. So we compared it with the F110, E110 alloy performance. And as you can see on the right-hand side, our new materials are much better when it comes to corrosion resistance, so better resistance to any folding, also higher fretting wear resistance of our coating, and last but not least, also strengthening of the underlying material. So there is the zirconium alloy. And when it interacts with the fuel and encapsulated fuel. So when you look at the corrosion resistance, it is much, much higher. And I will summarize the numbers at the end. But when it comes to behavior of the fuel in emergency situations, so when you have high temperature oxidation, the new material has dramatically better performance. It's more resistant to high temperature oxidation. So in any case, there is an excellent resistance towards high temperature oxidation, the material is strengthened, it is stronger. So if there's any ballooning happening in an emergency situation, as you can see on the slide, the ballooning effect is much smaller in comparison with the standard material. So it lowers the risk of blocking the cooling channels, and it improves the performance of cooling in case of any emergency. What we will have to look into even further is better mechanical resistance, because in certain conditions there is a diffusion, interdiffusion, material interdiffusion and phase composition. That's what we'll have to look into, because it may complicate the situation. But we're speaking about heavy emergencies that we will have to look at. The overall outcomes of our testing is that the new material, the new coating of the fuel is much better in terms of its features than the existing material. So what I would like to highlight at the end, and I believe this is the right moment in my presentation when I should say it, when we hear ATF abbreviation in the world, well, it developed in two directions. First of all, we looked at accident modeling and simulation and accident tolerance. So we're looking at the causes of the causes of accidents and the drawbacks, the flaws in the existing model. So we looked at how the fuel behaves in heavy accidents and what consequences it may have, and if there are any leakages of nuclear material into the outside environment. And we found out that many of these concepts, if they should have real impact on the way the fuel behaves in accidents, they have a negative impact on the economy of the fuel cycle. So there was a separate branch of development using the same abbreviation, but tolerant was replaced with technology, so advanced technology fuel, which basically is nothing else than applying the same concept, but to a smaller extent, to an extent when it doesn't have an impact or a dramatic impact on the fuel cycle economy. But unfortunately, at the same time, it does not provide better protection in accident situations, but it significantly improves performance in standard operations. So if you have a narrow coating layer, it improves corrosion resistance in standard operations. It also improves the fraction resistance, but it will not provide proper protection when it comes to heavy accidents. So on this slide, what you can see is the outcome of modeling and simulation of an accident. So we've used a FRAPCON FRAPTRAN codes with inbuilt implemented chromium coated zircon. And you can see the properties, the time to rupture of the fuel coating increases by 20%. The cladding deformation is by 3 to 10% lower. And what is very significant is the oxide layer, the oxidation layer, and hydrogen production that is nine times lower. So you can see quite clearly that if we apply this approach, this concept, to the extent that provides sufficient protection, then the impact on the subsequent consequences is again significant. So as I said in the beginning, last year we completed the stage of non-active tests, non-active testing, the in-pile testing. To some extent, it was financed, it was funded by a subsidy project. We implemented that in cooperation with the Czech Technical University, the engineering faculty, and nuclear reactors department of that faculty. In the next stage, we will get into qualifying and testing these concepts in an in-reactor environment. So we will select 3 qualified concepts, and they will be moved to the radiation stage, in reactor irradiation stage. So inside the reactor, we will be testing the claddings and coatings as a part of the project. And the project is being implemented as part of an OECD program called FIDEX. And there's one sub-project, as you can see, which is Czech. Well, it's not totally Czech because there are some Finnish and French partners in the core group. And as part of that project, we're going to do the irradiation of the pressurized samples of the cladding tubes delivered by our company.
And subsequently, we will test the mechanical properties of the irradiated cladding in hot chambers. And at the same time, this project also focuses on the qualification and qualification of the irradiation conditions, and also testing, examining the transferability of the experience and knowledge gained in the LVR-15 reactor to real-life commercially operated reactors. Because we actually have this ability to compare these two in a commercial reactor and here, because we have another project going on at the same time. So that's the next stage, the second stage of this project that we've already started to implement. And the third stage would be planned irradiation in a commercial, of this material in a commercial reactor. That's planned for 2023. We would like to insert the material clusters with our own newly developed ATF concept, yet without the fuel, but within or inserted within the active zone of the reactor, so that we can confirm that the cladding is really usable in industrial practice on an everyday basis, so that we can offer it commercially on the market, either to the manufacturers of the fuel cells, or perhaps whoever would be interested in enhancing their fuel cladding. To conclude my remarks, I'd like to say that the concepts of the accident-tolerant fuels, the activities, in fact, in this area will be celebrating the 10th year. It's already 10 years in the making. And that is something that made us revisit the main capacities of research, or primary research, particularly in the United States, of not just the cladding, but also the whole chain of the fuels. And today, the concept in practice, or the reality in practice, is such that if you can't really offer a fuel that is ATF criteria compatible, well, in that case, it's very unlikely that you would get a contract, because you don't have a fuel that would be acceptable to your customers in the future. We started off by chrome-based coating, and we turned out to have 3 different variants, 3 different concepts, and one of them, at least, looks like a good candidate for the ATF, a truly accident-tolerant fuel. The other 2 are more on the side of the advanced technology fuel. But generally, these efforts are put in practice so that we are developing what we can. And we started off the active irradiation. We will start the active irradiation of the product in the active zone. That we will start in this year, and in 2023, as I said, we'd like to hopefully start marketing commercially this first material. Obviously, this will tie in with the contracts and certification efforts that will be necessary for this, also certification from the regulatory authority. Other than that, I'd like to say that we continue our cooperation with international partners, be it projects within the IAEA or EU or NEA. Our company is a full-fledged member of the FIDEX association. So that's it from me. Thank you for your attention, and I do apologize for the technical glitch with the connection, and I'm open to any questions you might have. Thank you for your interesting presentation. We are running out of time, unfortunately, because in 15 minutes time, we have another section starting. So I'm going to have to cancel the Q&A session. So if you have any questions you'd like to ask, please catch up with the individual presenters and talk to them individually. Thank you very much. This is it. And I'd like to thank you as well. You know, the Q&A session would be a nice to have thing, but unfortunately we can't do it because of the time constraint. So if you can't catch up with the people who've presented the material here, just let us know and we'll put you in contact with them. Thank you for your understanding, and we will resume in 15 minutes from now. Yes, if I may say, I will be available on site in 3D if people want to talk to me. Thank you.
Termín zahájení naší sekce se už posunul proti původnímu plánu, ale zatím ne o moc. Zatím je to teprve 2. minuta. Tak dovolte, abych tedy představil chairmana další sekce, kterou teď si vyslechneme. Kolega Miroslav Picek.
To jsem já.
Kolega Picek je stejně jako já původem ze školy jaderné strojírenství, kde jsme oba strávili.
So Mr. Bicek will facilitate the next session. We've spent most of our professional lives together in Škoda JS. So despite the fact that many of you are still outside in the hall getting coffee and refreshment, we will have to start because our agenda is so full that we simply cannot afford any delays. So I will ask the facilitator to strictly stick to the time. Okay, thank you. And let me start the 4th section, focusing on the decommissioning and long-term nuclear waste storage. Of course, we can shorten the presentations. We can also shorten the break, which probably will not be acceptable for many of you. So I would like to ask Mr. Herbeck from Rzesz, who will speak about the advanced solutions of the nuclear cycle. And you have 20 minutes, including questions. So good morning. Thank you for introducing my presentation. I will be talking about the research that we do in the Rzesz Center, and that concerns the nuclear fuel cycle. The main objective of our research is the support of the backward part of the fuel cycle. We also have analytical support for water management and waste management. We also develop analytical methods to detect the isotopic composition of the samples. We have research based on the optimization of active and toxic and dangerous waste. We also look at the processing of burnt out fuel, and we have experimental research of material of salt reactors. I will speak about the individual parts of that presentation. So our center is split into individual labs, and each of the labs focuses on one of the areas that I mentioned in the beginning. I guess that doesn't have to be commented. We simply have 6 labs, and each lab working on its own area, and we complement each other. The first area focuses on research into water management. Our colleagues are able to do chemical analysis of ultra clean and processed waters originating in energy. What you can see at the bottom is the cleaning process, where we try to eliminate heavy metals from various materials. We also have an analytical group which has various devices at its disposal. They use those devices and facilities to analyze various waters. For example, a device identifying anorganic ions, or on the right-hand side at the bottom, it's a spectrometer, which allows to monitor corrosion in various circuits. So that group also provides support to the operators of power plants, standard power plants, as well as nuclear power plants. The group also researches into sorption and ioned materials. They use various methods to test various ionics substances to improve absorption. These are images from a microscope, and those images document how they evaluate the ionics substances. For example, they measure the pressure loss during absorption, and also research into various methodologies for the application of absorption materials and increasing their efficiency. The next group deals into optimization, processing, and liquidation of hazardous waste. And they run two technologies. The first one is an experimental technological line, ETL, which focuses on the decrease of volume of fluid waste. That is a big problem when we have fluid waste, be them radioactive or hazardous in any other way. We want the volume of such waste to be as small as possible. So that's what our colleagues are looking at. They look at, for example, vacuum, increase of density, and then crystallization and solidification of the dense waste into polymers. The second technology that this group runs is called an experimental technological facility, molten salt oxidation, MSO. So the waste, be it solid waste or fluid waste or semi-fluid waste, is injected below the level of molten salt together with oxygen or air, and at high temperatures there is an oxidation process resulting into the burning of organic components, and the gasified organic components are caught in the melted salt. The advantage of that technology is that the type of the salt that we use to catch the hazardous materials can be recycled thanks to the second technology, that experimental line, where the technological salt with the remains of the hazardous waste can be dissolved in water, and it can be processed in the experimental technological line, ETL. And what comes out is a small volume of waste with small content of salt and large content of the waste of those hazardous particles. And the salt is reusable, so we can then take it and use it again in the MSO. And since we're dealing with the nuclear fuel cycle mainly, we can use both of these devices with simulated nuclear activity. So we can simulate the activity of various substances that are used in the primary circuit, for example, in a nuclear power plant. But both of these facilities work in a non-active condition, non-active operation.
On the left picture, you can see the solidification of the oxygen in polysilicon, and that's in the experimental technology line that we refer to as ETL. And on the right, this is the salt molten from the MSO, the molten salt oxidization process. So in the next step, you would be able to recycle that salt and reuse it. Next, we also have a laboratory of element and isotope microanalysis. The reason being that when we do something, we want to be sure about the isotopes and the elements being involved. The photograph on the bottom left shows you a piece of equipment, a device called SIMS, which allows you to do isotope analysis in micro levels of the isotopes on the surface of solid objects. It's a very precise piece of equipment. It's got a transmissive electron. Then we have a transmissive electron microscope that's on the bottom right, on top right, and the scanning electron microscope that was in the bottom right. Now, this is the field my colleagues are involved in. And I'd like to draw your attention to the small triangles in the upper picture there. That's the biofilm that developed during an anaerobic corrosion of some materials. That's what other group of our colleagues is involved in. And that's a group that focuses on research connected to the spent fuel storage sites. So these two groups work together. One does an experiment and the other one might add analysis, for instance, an analysis. We also have another department focusing on advanced corrosion-related research. That's the other group I talked about. So corrosion research in relation to spent nuclear fuel waste storage sites is exactly what they do. And they have anaerobic boxes to provide an environment for the corrosion testing, and they also cultivate various microorganisms, and they study the microbiological corrosion of various materials that get used in the spent fuel storage sites. These pictures are taken from the scanning electron microscopes. Biofilm layers, thin layers of that developed on material. This is what you get if you let a material degrade over a long period of time. And this first picture on the left looks like somebody is standing on a piece of rock. It's not that. That should be the, let's say, the interface, the border line of that sample taken. On the next slide, you can see pictures of various samples from corrosion, because corrosion develops in a number of ways, and we also test the various exposition times. The same group is involved in advanced material research as well. This is where we test the materials to be used in the deep storage sites for spent fuel. And in particular, they are involved in researching geopolymer materials, testing tensile strength. They have a hydraulic press, They prepare various types of samples. They assess and evaluate the degradation and degradation rate of materials, but at the same time, they also test minerals. You can see sample of a mineral that was injected with liquid, and based on conductivity measurement, you're able to determine the speed of this liquid seeping through that mineral. And this allows you to evaluate the suitability or not of that particular mineral. What we also do is corrosion and material tests in fluoride molten materials. This picture shows you, it's a microscope picture of a sample where the material was exposed to fluoride molten material. And our colleagues focused on how and where corrosion develops. What we do is stationary and dynamic corrosion tests, short-term tests as well as long-term tests for the Generation 4 reactors. On this picture, you can see the what is known as the FLIBE, F-L-I-B-E loop, which is an environment, laboratory environment that allows us to test the behavior of the salt and the materials exposed to the salt. Why I'm talking about this in my presentation is because our colleagues in the Czech Nuclear Research Center are involved in developing the energy well reactor, and this particular research simulates the processes that will be at play in the primary circuit of that power plant. The FLIBE salt is planned to be used as the coolant for that primary circuit. In the top left picture, you can see boxes with the salt, and that's during a long-term testing procedure. And on the left bottom, in the left bottom picture, you can see a sample of that salt. And you can also see the microscope images of the corrosion process. Last but not least, we are also involved in research in the field of high temperature molted material. And in this particular section of research, we focus on the accident-related processes of nuclear facilities. This is in relation to the Fukushima accident, and we can reach a temperature of 3,200 degrees Celsius. That's not the limiting temperature. We can actually reach a higher temperature, but we would not be able to measure it. So if you can do something in terms of measuring temperatures above that level, we will certainly be able to model it in this environment. Now, the device you can see on the picture is called cold cup, or melting pot, rather, cold melting pot. The cold melting pot is a similar thing like a blast furnace for iron, but this obviously is cooled. So the temperature might have, the temperature of the wall could be 100 degrees Celsius, but the temperature inside might be, let's say, 3,000 degrees Celsius. So it protects the molten material and protects the outside environment. And that allows us to conduct experiments simulating the melting core, the melted core of the reactor. It's uranium oxide plus zirconium oxide are molten together, and you can simulate what happens. We also try to pour the molten core on the sample there, and we were studying what would happen during the accident if that should actually happen in real life condition. In the middle, you can see the picture of the hot core, molten core, being poured onto a sample. Usually the temperature is around 2,800 or 3,000 degrees Celsius. We then analyze the materials using electron microscope. But with that technology, we're also able to vitrify glass, and we also intend to work on that front. It'll be an addition to our activities. We can let crystals grow in this way. So that will be it from my point of view. And if you have any questions, I'm happy to take them.
So if in case we don't have any questions from the audience, I have a question. You mentioned that you do microbiological analysis of corrosion. We do it as well in Škoda, and we do it together with the chemical university. And those microbiological analyses are focusing on a specific material of the cladding material, of the encapsulation material. And my question is whether you focus on a wide range of materials, or whether you deal with the material that we've already agreed on as the best candidate for the material. It's S355J2H. Well, I don't really want to go into details here. My colleagues are looking at various materials. I'm not sure. I'm not certain. I rather look at the very last area that I touched on, that is nuclear accidents. So when it comes to corrosion tests, I am not really able to answer now, but I can give you contact to my colleagues that will answer your question. Do we have any further questions? No, so I will have another question. You mentioned that you're able to detect cations in industrial wastewaters in very small concentrations, micron concentrations. So if you went to that wastewater outlet into the river Bečva, would you be able to identify the pollution faster than the hygiene station workers? Well, yes, I'm convinced we would. Well, why weren't you there? Okay, that was just a question to close the discussion. So if we do not have any further questions, I would like to ask Mr. Tomáš Fischer, who will talk about the current state of affairs when it comes to decommissioning of nuclear power plant T1.
Takže ještě raz dobrý den. Doufám, že se počujeme a vidíme.
So once again, good morning to all of you. Hope you can hear me and see me. So my presentation is about decommissioning of nuclear power plant A1. So I will try to show to you the main and most interesting activities, those that we already finished and those that are still in progress. So these are major milestones for those of you that do not know the history of A1, a nuclear power plant. So you can quickly read that. What is what is most important is that the construction of A1 nuclear power plant was done by the state of Czechoslovakia. So the country, did or put together all the projects and the construction. Of course, it was in cooperation with the Soviet technicians and scientists. It was in the 60s of the previous century, so it was admirable that such a small state, such a small country was able to put together such a big project. The operations were lasted 5 years, and during the operations there were various shutdowns because of defects manifesting themselves that needed to be repaired. But of course, the power plant was also gradually upgraded and technological systems were upgraded as well. So these are the basic technical parameters. What was important in relation to the operations or the decommissioning that we're doing now is that CO2 was used as a cooling agent, the coolant. The moderating agent was heavy water, and we used metal uranium as the fuel. Using CO2 as a coolant proved to be problematic, mainly because of the steam generators, because due to various leakages, the secondary circuit was contaminated, and that has had and still has an impact on the decommissioning process. What you can see here at the bottom part of that image is an outlet pipe or pipes that let the gas into the steam generator, and the cold gas from the steam generator was led back to the top of the reactor. And I will show you more details in the presentation when I speak about the decommissioning of the cooling zones and the steam generators. So these are the two most significant events in the power plant that had an impact on the operations as well as decommissioning of the plant. After the second event, the technological systems were damaged to such an extent that repairing it would not provide the required rate of return, because at that time a new nuclear power plant was already being built. So the repairs were not performed. As for the second event, the fuel cell got into the technological channels and CO2 started to leak from the cooling circuit. The operators managed to seal the crack, but there was a tragedy linked to it because CO2 is heavier than air. It reached lower floors of the facility and 2 operators suffocated because of that. So during the second event, the second emergency, the cooling channel got stuck due to a spilled silica gel. When assembling the fuel cells, there was a partial meltdown the cladding was disrupted, and the whole circuit of heavy water was contaminated. So with that event, the operations of A1 was brought to an end. And in 1979, it was decided to close down that nuclear power plant. And as you can see on the time chart, it took 22 years from the end of operations to the start of decommissioning of that power plant. It was for justified reasons. And only in 1999, the last block of fuel was brought back to Russia, and that was the last condition that had to be fulfilled to start decommissioning, because at A1 the burnt out fuel was stored inside the nuclear power plant in a repository. It's a difference between A1 and A2 because A2 already had an interim storage of burnt out fuel.
Okay, we're getting to the individual specific type of activities that we implemented in the decommissioning process. I will only focus on the substantial thing, that is the decommissioning of the storage room for used and intended to be used for storage of spent nuclear fuel. You can think of it as a set of rooms with the storage pool down there. This is where the rods are suspended and located. There are 4 quadrants with channels, and in between them these capsules are suspended. The important thing to mention is that the water in this storage tank was removed, pumped away from during the decommissioning process. It was about 560 cubic meters of water, and all of that was processed. Also, the sludge from the tanks were put into a cemented, into the new tanks, and this manipulating device, you can see, allowed us to remove the sludge. So what you can see is the bottom of the cleaned up pool. The sludge that was pumped over into the new tank or tanks have been processed, all of them, and put into a cement matrix. And in that form, they are ready to be deposited in the Mochovce Central Nuclear Spent Fuel Depository or Storage Site. Another important activity was the construction of the site I mentioned for storing spent fuel in Mochovce, Slovakia. This was also made possible by the new legislation that was put in place. The storage site is part of the Slovak national system of the spent fuel storage sites. The capacity being roughly 48,000 cubic meters of this spent fuel. The A1 would have provided about 22,000 cubic meters, and there's 9,000 cubic meters reserved for the other unit. 36 The remaining 36 altogether would be 1,000 cubic meters would be reserved for the nuclear sites in Slovakia. So what we store there is usually bulk material, bulk waste that is turned into rubble. This type of waste is put into large size bags. Roughly of 1.1 cubic meters volume each. The space between these individual bags is filled up with earth and then compacted. The storage site proper is based on a system of drainage canals and sealing material. That's to make sure that there is no impact on people living nearby and the environment, of course. So this is where the storage site is located, and the top of the storage site underground is covered on the ground level with this type of hole. And then there is an insulation layer or insulation layers plus drainage layers. And once a particular section of that storage site has been filled up with the waste, then you move over to the next one. Now, this is a slide showing pictures from the decommissioning phase proper. These were the feeders, the feeding machines that were used during the operation time of this reactor to change fuel cells or fuel rods. There were, as you can see, 2 feeders on the A1. They were dismantled from top to the bottom and turned into several large dimension components or pieces. And then there's a special unit that was built on a railway carriage with a container and on one side, and the control operators stage plus air technology, etc., etc. And the other side of this unit consists of a saw, a large-scale saw that can cut pieces into smaller chunks that can be then transported and handled as standard pieces of scrap iron. You can see the carriages of the feeder machines. One of them still serves in the original condition as an exhibit in the museum section of that one of the institutions. And just to give you an idea, the carriage, the undercarriage, the weight of the undercarriage was about 42 tons. So really a very bulky piece of equipment, very heavy. And if things go well, as has been the case so far, on the 5th of January, you should be able to take a look at this exhibit, or perhaps some more exhibits as well, because there'll be an information center on the site, which will show visitors the history of the construction, operation, and decommissioning of the A1. You can see on the pictures on this slide the individual phases of the decommissioning of the cooling system in the primary circuit. This is a CO2-based system. That was an independent, self-standing process unit with its own water distribution system and CO2 distribution system. That was used to cool various pieces of equipment like pumps, compressors, and etc. The ones that were installed in the primary circuit. And this part is for the secondary sector. Secondary circuit. Point 4, that's the dismantling of crane or removal of crane. That's the portal crane that was installed up on the roof of that hall and was used to install the steam generators during the construction period. And this portal crane was dismantled as one of the dominants, one of the significant features of the A1 unit, because you could see it from a far distance. That portal crane had a weight of about 30 tons. But to dismantle it from the top of that roof, we had to have crane truck with load capacity of up to 60 tons, or plus 60 tons. And using counterweights, and this was balanced out in order to dismantle and remove the portal crane on 7 trucks.
So I also mentioned the decommissioning of a long-term repository. So this is a continuation of that activity. It's an ongoing decommissioning activity, the decommissioning of the capsules in encapsulation of the fuel. You can see the picture of that on the slide. So we took it out of the long-term repository and handled that storage or that encapsulation, moved it to a manipulation site when we cut it into pieces to allow for decontamination and further processing. So 783 pieces, out of which 485 pieces have already been processed. So we still have some 300 pieces to process. So decommissioning of A1 nuclear power plant did not include only dismantling of technology and systems, but we also have to remove various buildings and structures. And we also monitor the impact of the decommissioning process on the local inhabitants and on the environment. You've exceeded your time already. Time. How much time do I have? Okay, so for our foreign guests, we can add 5 more minutes. So what you can see on these images is the result of the cleaning of underground water, which we pumped out, and that pumping of the underground water is to prevent the leakage of contamination into that water and affecting the wider environment and inhabitants. So during those pumping activities, we got to a situation when we reached below levels of underground water, the levels which are lower than the regulation sets. So we would not be able to continue pumping, but we argued that we're doing it for the inhabitants to protect it, to protect them from any negative impact. So to move to what is really interesting and what we're doing at this moment. So the next two slides describe the decommissioning of the cooling circuits and related decommissioning of steam generators. So you can see the decommissioning of the primary piping, the flanges in individual sections, and then the pipes that were leading or feeding the cold gas back to the reactor. A1 had 12 hot pipes that fed the hot gas into the steam generator. And at each pipe, there were two section flanges. And when the gas reached the steam generator, there were two turbo compressors that fed the gas into the generator, and you can see the decommissioning of the section flanges. So decommissioning of steam generators. At this moment, we're decommissioning generators 3 and 4 because these steam generators are located in space which has the lowest radiation level. And we're also decommissioning one of the turbo compressors. The other one was still in operation, so we could not start the decommissioning. So we were gradually cutting the pipes from the top to the bottom. We're preparing for the completion of that decommissioning. So as you can see on the left-hand side on those pictures, we're doing cleaning to be able to assemble technology on the site to do the decommissioning of those pipes. We have a special cutter, a cutting device, which is fixed onto that pipe, and it can cut the pipe in one direction, and by performing 2 cuts, you can take out a roughly 80 centimeter long piece, and then we will do standard decommissioning handling of those pieces of pipes. So at present, we're performing the 3rd and 4th stage of decommissioning that should end in 2024. And we're already working on the documentation and database of those parts of A1 which will be decommissioned in the next stage. We're doing it in advance to have enough time to acquire all permits. So the permit of the regulator and the supervisor, and also a permit acquired from the European Commission, because we have to send all the documentation to them as well. And we have to have an environmental impact assessment with a positive assessment, of course. So this is the basic legislative process which we'll have to go through in the next stage as well, and we have to be ready for that. So in this table, you can see the most fundamental steps that we have to go through to have all the permits issued and to be ready for the final stage of decommissioning of A1. So these are the main steps, the main parts that will await us in stage 5 of decommissioning. So the last 4 parts of the steam generator will have to be decommissioned, then the reactor and other connected devices and other devices that will be used in the previous stages for the decommissioning process itself, and then also handling of nuclear waste. So these are the most important parts or units that will have to be decommissioned in the upcoming stage. So that's all on my side. Thank you for attention. Do we have any questions? Thank you too. Do we have questions from the audience? And please wait for the microphone. Mr. Neumann, so what happened with the 57 tons of heavy water? Well, heavy water was cleaned and it was sold to Romania, I think, or Bulgaria maybe. So we did not keep it at the A1 power plant. It was sold to abroad. So if we do not have any more questions, and thank you, and regards to Slovakia. No more questions? Okay, so thank you once again, and goodbye. The next presentation is again from our colleague from Slovakia, Mr. Peter Krupa, who will talk about the current state of decommissioning of V1 nuclear power plant. So the floor is yours.
Hello, good afternoon. I don't know if you already see my presentation. Hello, we can hear you, but we can't see you nor your presentation. Hello? Yes, we can hear you, but and can you see my presentation? You are there. Hello, everybody. I'm sorry. I'm going to have to. I'm going to have to interrupt there. No, we can't see the presentation.
Dobrý den, jenom jestli vy už jste nasdílel nějakou obrazovku?
Ano, ano.
My to tu nevidíme vůbec, ani že byste to jako sdíleli.
No jste mi hovoril, že to je vidět.
Ne, no, oni řekli, že vidí vás, ale prezentaci bohužel ještě nevidíme.
Je to možné teraz?
Jo, teď už to vidíme.
About now? Yes, we can see the presentation very well. So, back to you. Let me just give you this housekeeping remark. your time will be up at 12:55. We're slightly behind you. Okay, thank you for letting me know. I will try to use that wisely. Ladies and gentlemen, let me give you a brief overview of the decommissioning process of the V1 unit in Jaslovské Bohunice in Slovakia. I will focus on the current state of play and also about the future steps, future projects that we plan to implement. As some of you may already know, the decommissioning of the V1 is divided into two phases. The first one, up until 2014, was focused on the decommissioning of the unused construction structures and construction units and the equipment. And the second phase that started from 2016 focuses on the contaminated equipment and units and the nuclear island. Altogether, this is funded by the Slovak government and particularly the EU sources. The decommissioning process is divided into individual projects that tie into one another, and we've completed 62 projects so far. At the moment, we have 8 projects underway, and we've just completed an important project this year. That's the decommissioning of the primary zone equipment. So these were the systems that were no longer useful even in this stage, in the subsequent stages of decommissioning. We also have a project of correcting the system of electrical supply. That's a project consisting in the change of the supply system following the change of our status as a consumer rather than producer of electricity. We also cooperate with the Research Institute and Research Center in Rzeszów. And this project is following up on the characterization of the whole location of the site, and also follows up on the effort to create a database with all the characteristics of the projects for decommissioning. Then there is another project for decommissioning of changing the metallic section, metallic part of radioactive waste. And it's tied in with the Technological Center in Jaslovské Bohunice, then the modifications to the individual sections of the power plant. So that's where we stand at the moment, very briefly. Now, as regards the modification to the power plant, it was a major effort, and it was something that was necessary in order to modify the power plant to the needs suited for the process of decommissioning. 4 sub-projects have already been implemented and completed. These were the construction and technology or process modifications. Think of it like manholes being changed, individual lifting equipment being installed, etc., in order to support the subsequent projects. The next project consisted of modifying the production of generation of cooling water. And the biggest volume of work was in the field of modifications necessary for the intermittent storage site for the spent nuclear fuel. Part of the functions was conducted by the V1 nuclear power plant. So we had to put this modification in place in order to become independent on the V1 original nuclear power plant, because it is being decommissioned. We are working on 5, 6, and 7. That's the modification to the removal of contaminated waters from the V1 site, and also building the site or station for feeding and also installing the piping routes for the regeneration and decontamination solutions. Last week, we tested the comprehensive system for removal of the contaminated waters. And once this process has been completed and successfully certified, then we will step into the next phase to get the full decommissioning approval. As regards project listed here and under number 6, we've actively tested this already, and this was based on the approval from the regulatory authority for nuclear facilities. We have an approval for a 2-month period, or I should actually say that it normally takes 2 months, but the licensing process gets delayed for all sorts of reasons. So we got the approval sometime in August, and currently this sub-project is underway. As you can see on this picture, it's a modification to the construction site of the contaminated water system. These are 2 650 cubic meter tanks that will be used for the storing the contaminated water from the site. And we plan to complete this sub-project in March next year. So we are evaluating the comprehensive passive and active testing, and then the certification or licensing process that is in the hands of the regulatory authority. The next part of the decommissioning stage is the dismantling or removal of the large size components of the primary circuit. This project is focusing on the dismantling and removal and fragmentation of all the contaminated and activated pieces of equipment in the primary circuit. And in order for us to be able to enter that stage of decommissioning, we've had to do a lot of engineering work and provide a lot of documentation. 99% of that has been already completed. Based on these projects or sub-projects, we've built a couple of work sites dealing with the individual operations, such as cutting, either wet cutting or dry cutting of the individual large-scale pieces of equipment. And at this stage, all of these work sites are fully functional, and we are already processing these large-scale pieces of equipment.
So to sum it up, the engineering activities are finished at 99%, be it decontamination, the activated components and other components. When it comes to the dismantling and other activities, fragmentation and so forth, we've completed roughly 75%. If we consider that all activated components, the basket from the active zone, the connecting rods and the controlling rods and all the other components, all of that is done in the wet cutting pool. That is the third image. And we have a site in the in the control room or plant room. So all of those segments were moved to the plant room and were doing fragmentation, which is on the right-hand side. I don't know whether you can see my pointer. So the next image documents the wet cutting, the dry cutting site, the main circulation pump and its fragmentation, and the fragmentation of the pressure vessel of the reactor. And on the last image, You can see the inner reactor components which are undergoing fragmentation. So the main activity is the processing of the metallic material and the dismantling and fragmentation of active components. So this slide sums up all the components that we've already processed. So the connecting rods, all of that has been fragmented, and the absorbers, that's done. The shielding containers, that has been segmented as well, or fragmented as well, and we're doing the 5th cut on the 2nd block. So we're up to 15% of completion. We're at this moment, we have separated the main vessel of the reactor, or are planning to separate it vertically into 11 blocks, 11 parts, and then we will be handling those parts further. Then the active zone holder has been fragmented almost up to 100%. We're fragmenting the bottom and the active cladding on the 2nd block at this moment. The 1st block has been completed. So that's these were the active components. As for the contaminated components, all the steam generators have been dismantled and moved to the plant room. 6 steam generators have been fragmented already. At this moment, we're fragmenting the 7th steam generator. The primary pipeline has been completed. The fragmentation has been completed. Also, the volume compensator has been completed, and at this moment we're cutting the main circulation pumps. So we've cut already 10 out of 12, and the main closing flanges have been cut as well, 24 pieces. When it comes to the radioactive waste repository, or we call that Mogilnik, or the location is called Mogilnik, we have already fragmented the connecting rods and the absorbers, and at this moment we're fragmenting the channel that was used for measuring of the neutron flow, and that should be finished by October 2021. So these are the works on fragmentation and decontamination of the main parts of the V1 nuclear power plant, the primary circuit. We try to decontaminate all the contaminated material. We have decontamination lines, and those materials that are activated and that cannot be stored in our regional storage in Mochovce are stored in a central integrated storage for activated nuclear waste. It serves 3 functions. First of all, we're storing the barrels. It's sort of a buffer storage or interim storage before further processing. We also have a certain volume of highly activated material that cannot be stored in the regional storage site in Mochovce. So that material is stored in this iron in these iron containers, and we have 3 levels of activation. We have 80 millimeter, 150 millimeter, and 210 millimeter thick wall containers. And we also have special carrier baskets for various other materials, depending on the isotope composition. So that material is is waiting for further processing and decontamination. So this is the central repository of burnt fuel. And when it comes to current works, what we're doing now, what you can see on this slide is a dismantling of water biological protection that was successfully dismantled on the first block, and we're demolishing the activated concrete at this moment. So that was a part of the biological protection system. And we're continuing work on the second block. We're dismantling the isolation from that water biological protection system, and then we will do fragmentation. Of course, all of that is done remotely. What you can see on the slide on the right-hand side are demolition works of various structures and buildings. That picture was taken during the preparation stage when we had to do certain preparation steps in the hall, in the structure. So as I have said, we have sites ready for decontamination and fragmentation. We have decontamination vessels and ultrasound fragmentation device. We have a relatively high success rate when it comes to returning material to the environment. Of course, decontaminated material. We have released 98.6% of material that was decontaminated and returned to the natural environment. So at this moment, we have some 2,500 tons of material already processed at the decontamination sites, and roughly 1,500 tons were returned back to the natural environment. So that's our plan of what we do with the material. So another problem, which is not directly related to the V1 decommissioning, but it relates to other types of materials that can be melted and released back to the environment. So various metallic materials, and we have a special site for processing of those materials. So we prepare the material, we melt it, and then that melted metal is cast into forms and cooled down. And then we have a separate station for measuring the parameters of those castings. So at this moment, we completed the non-active trials. So based on the pre-comprehensive and comprehensive and non-active trials, we put together a list of defects and flaws that we have to eliminate and we have to correct. And in parallel or simultaneously with that, we're working on the licensing process. So we filed an application for active trials, active testing. And once we receive a green light for that application, we can continue with active trials. C8B02 is another part of the project. There's a huge volume of contaminated metallic material that we have to handle, that we have to process, and all of those sites are located in the controlled zone. So we try to also use a hall that Škoda used to use for its operations, and we turn it into a storage site.
Another interesting sub-project that is part of the D42 is the dismantling of the systems in the controlled zone, which of course is coordinated with the projects I've mentioned, but is focused on the systems that we no longer will need. That's the air systems, fixation of the sludge from the individual tanks, decontamination and fragmentation and further handling of that material. So that's another huge project that is underway. We're also dismantling the doors and gates, large size components of this type. The next part will consist in decontamination and demolition of the construction units of the structures there in V1 and bringing the premises to the original state. So that's something that consists in wet cutting and removing the pools. Then this will be followed by the decontamination of the structures, and then essentially getting the place cleared off for demolition and following obviously radiation check and monitoring then the final landfill and landscaping work subject to regulatory authority approval. So you have the basic elements of the decontamination process, dismantling of large size components in the primary circuit, then dismantling of the systems in the second part, and the decontamination and demolition of the structures. That is the last project that is indeed underway. There are a couple of external factors that we need to put into the equation, which is getting the financial discussions, then getting the extended permit and approvals for this, and the administrative side of things with the necessary extensions to the individual steps and approvals. Now, this is the critical path, and this is the last slide of my presentation. All these activities are coordinated, and all of this is planned to be completed by the end of 2027. But the main part here of our work consists of the projects that will be essentially fragmenting all the large size components, which should be completed by 2022. Then decontamination and the wet cutting decontamination. Then the wastewater treatment and processing. Then the metallic waste processing that should be completed by April 2024. And subsequently, the D47 sub-projects can follow as decontamination and demolition. So that is the state of play of the decontamination project of the V1 in Jaslovské Bohunice at the moment. If you have any questions, please go ahead. Thank you. Thanks to Mr. Krupa for his very interesting presentation about how they approached the decommissioning project at V1. Do we have any questions, ladies and gentlemen? All right, there being no questions from the auditorium, I will take the liberty of asking one question. You mentioned the decontamination and decommissioning of Mogilnik. Will you be using cement, or will you be decommissioning it as it is now? Well, let me put it this way. The Mogilik, it's defined as the storage site R115, I think. The absorbers have been removed. The neutron transfer canals have been removed. We will subsequently demolish and fragment that part, and the 399 steel pipes will be completely fragmented and removed from the site. And Mr. Zebor has one more question. Thank you. Yes, one more question about the neutral transfer canals. How do you actually get rid of them? They are pretty large. It's essentially looks like a huge pile of cables, and using the manipulator, you pull them out, and the VPK shielded container you put them there by cutting them into small pieces, like if you had wire cutters and cut these long wires into small pieces, and it's you cut them into pieces, you remove them, cut them into small pieces, let's say 20 to 30 centimeter long pieces, then it falls, they fall down into the shielded container, and then you remove it and dispose of it in a standard way. Okay, one more question there. Miroslav Kavalec is my name. I'd like to ask you this question. How will you handle the austenitic stainless steel piping from the steam generator? I suppose it would be decontamination, and will you release them for further use, or what will be the other way of doing it? We had this previous project of decontaminating the primary circuit. That is why and how we removed or reduced the activity levels, radioactivity levels of the primary circuit. After that, we've put these into barrels, and I don't think we will be doing any further decontamination. So the first decontamination has already taken place, and I'm sorry, so it'll be used as a raw material. So if you want to use it as a raw material, recycle it, you can just melt it and then resell it. Indeed, that's exactly it. Thank you. Any more questions? I'm really interested in this one. I'm going to ask this question. If during the decommissioning of V1 there are very hazardous, highly hazardous toxic waste produced, will they be stored in the central VVK storage site, or will they be stored somewhere else, or what do you do with them? I don't know if you can see this. This is the integral storage site with 4 modules, if I'm not mistaken. And as I said, one unit, one part of it, depending, you can do your calculations. After 20 years, this will be released. The sections that can't be released or stored is put into these shielded steel containers, traditional cement container plus a basket plus the fragment in there inside and the very core. What happens if you've removed the pressure vessel from the pool that is underwater? The individual fragments are put into baskets, and then they are shielded by a bell-shaped structure. Then you put them into a container packaging center, if you like, and then you store these fragments in this heavy metallic container with different wall thicknesses, different sizes. So that is the type of process that we use for this, and then they'll be decided upon what we do next with it. Okay, thank you very much. That was interesting. Unless there are more questions, we'd like to move on to our next presentation.
So the next presentation will be by Jaromír Sud from the Radioactive Waste Repositories Administration. The title of the presentation is The Role of the Administration SURAO in the System of Handling of Radioactive Waste in the Czech Republic. So good afternoon. My name is Jaromír Sud. I'm an employee of SURAO, the Radioactive Waste Repositories Administrator, and I was asked by my colleagues to present an overview of the role and the mission of our authority. So the role it plays in handling radioactive waste in the Czech Republic. And I will also describe the current activities of our authority. So the SURAO, which is the authority, the administrator, was established on the 1st of June 1997 by the Ministry of Industry and Trade, based on a newly adopted Act number 18 of 1997. And since January 1st, 2001, we became an organizational component of the state. As of January 1st, 2017, the administrator is governed by a new act. The legislative framework of our activity is set out by Article 113 of the Nuclear Act. And the legislative framework sets out activities such as the handling of radioactive waste and all the other activities based on the Nuclear Act. So we're in a situation similar to any other holder of a permission to conduct these activities. Our activity is financed from the state budget. We have a 3-year plan of activities. As for our mission, it is to provide a safe repository of nuclear waste in line with the nuclear safety and protection of human health and environment. The role of SURAO is to provide sufficient resources and capacity of the repositories and a selection of the final and backup location of the deep nuclear waste repository, and to guarantee transparency and information provision on the process of the selection of the site and construction of the deep repository. As for the subject of our activities, it's a long slide. You can see it. I will not waste time reading it. So it's the preparation, operating and monitoring and decommissioning or closing down repositories of nuclear waste. So institutional control or supervision of radioactive waste repository, then also handling of radioactive waste and adapting the radioactive waste to a situation when it is suitable for a deep repository. Then we also administer fees for the storage of radioactive waste, or rather handing over the radioactive waste to be owned by the state for storage. And then we also supervise the free reserves of the holders of the permit to generate nuclear waste, and also various other activities relating to the identification of nuclear material when we're not able to identify the owner, and that material becomes falls in the ownership of the state. We also provide financial finances or funds to municipalities based on our nuclear law that relates mainly to municipalities which were identified as potential sites for the future deep repository, or municipalities where interim repositories are already located. And we also provide subsidies to liquidate old radiation burdens based on a proper section of the Act. At this moment, Surao operates 3 radioactive waste repositories. We're monitoring the only closed down repository at Hostim, Uberona. We're also selecting the location and preparing the construction of the deep repository. We also conduct research and development when it comes to safe depositing of radioactive waste. We also have a testing operation of containment materials. And we also provide other activities such as creating provisions for nuclear waste storage. And we supervise the holders of the permits to operate repositories of 3rd and 4th category. I don't know whether you can see this table, but that table sums up the role of Surao when it comes to radioactive waste handling in the Czech Republic. So what it's all about, not everybody knows that Surao doesn't do processing of nuclear waste. We only store it in repositories. So, of course, Surao would not be able to conduct its activities without the holders of permits to handle and process that nuclear waste. So based on an act, and the activities performed with nuclear waste are split into handling, processing, sorting, and storing. So again, based on the Nuclear Act, you have to have a proper license or a permit to conduct these activities. So processing of nuclear waste is one of the activities stipulated by the Act, and that can be done only by holders of special permits. I think there are only 6 of them, or maybe 7 of them in the Czech Republic, 7 including Surao. So Surao does not process nuclear waste. We have the permit, we hold the license, but it's only for our own purposes. For example, when we need to repair certain fuel cells, or when we need to decontaminate components that were in operation, in active operation in the past, or decontamination of contaminated sites, but that was rather a question in the past. So storage in repositories, that is an activity that only Surao can do at present, and we have 3 storage sites. So Urao Hostim, that's a storage site, the only one that's been already closed down, and Surao provides supervision over that closed site. The most important site when it comes to our activities is a repository called Richard. It is most important because of its volume and importance. So the storage site Richard is very important to store the so-called institutionalized radioactive waste. It is a site located by Litoměřice in a quarry. It was opened in 1964. It is meant to store low and medium active waste. The volume or the space of the storage is roughly 10,000 square meters, but that's just a theoretical volume, because at this moment we've reconstructed other parts of that storage. We cannot use it now, but we're waiting for the license, so we have to change the proper documentation, and in a few months' time, the storage size should be extended, and we're expecting to extend the storage site within 10 or 20 years. So we're preparing a second stage of reconstruction of that site.
This storage site will be in operation until 2065. And by that time, there will have been another deep storage site in operation that should replace the rigid storage site. This is the rigid storage site as it looks now, including the green tower-like structure, which is a unit for testing the container units. And on the right-hand side, you can see the system of placement of the containers. It's a barrel-in-a-barrel, double barrel type of container. It's a time-tested, proven design. You put these waste materials into 115 liter barrels, then you put these into 216 liter barrels, and then they are stored in this way, in this fashion. Once these spaces have been filled up, these are known as storage chambers, and then you fill them up with concrete and you complete the filling up process with this material. The testing equipment is used for what is known as the container test site or test unit. These containers need to comply with Section 137 of the Nuclear Energy Act, and you test these containers by various mechanical and thermal properties, such as thermal properties, thermal test, pressure test, impact test, and etc., etc. And this is based on Czech standard 1725, ISO compatible or ISO harmonized. The next storage site is known as the site Bratrství, which is a former uranium mine in the former uranium mine complex at Jáchymov, some 450 meters of that uranium mine that was put into operation in 1974, and this is with the intention to use these for low and medium active waste with the exclusive content of natural radionuclides. The nominal capacity is 1,200 square meters, but currently the site's capacity has been used up almost completely and will be replaced by the former one that I talked about, called Richard. However, the decision has not been finally approved. We're not sure whether this will be the case for the Richard as the next place. It's a matter of philosophy. It's a decision yet to be made. Now, strategic or policy documents of the previous period mention the phasing out of this particular storage site called Bratrství. We think it'll be slightly adjusted in that the capacity might be slightly extended there, and the period would be actually extended beyond 2025. But still, the previous site I mentioned, will need to be used. This is the smallest storage site in the Czech Republic, and apart from the guards there, nobody else works there permanently. And it's the Richard storage site staff that travel to this site to do the regular checks. The yellowish building in the middle is the operations building, and then the greenish structure on the left is the entrance gate. Nothing fancy really, pretty simple, pretty basic. And now the storage site at Dukovany, probably the most important site in terms of this conference. That's inside, right on the premises of the Dukovany nuclear power plant. And it's surrounded by the Dukovany nuclear power facility, and we are dependent on ČEZ being the operator of that power plant, and they are an indispensable partner in operating these storage sites, spent fuel storage sites. Essentially, these are two lines of sumps, and these are intended for surface storage of these radioactive waste. This site was established in 1995, and as I said, it's designed to store low radioactive waste from nuclear power sector, on very exceptionally from research. So it's not only from the regular operations of nuclear power plants. And it is the largest storage site we have in the Czech Republic. Nominally, this is 55,000 cubic meters. In relation to the planned construction of more nuclear power sources in the Czech Republic, there is an idea that there'll be another 2 lines of containers or containment sumps built next to the existing ones. So this is the open storage sump for the nuclear waste, again in the same types of barrels, and you store them using a crane, and then once these have been filled up with the containers, you fill it up the rest of the space with concrete, with cement. I've also included the layout of the storage site, the tiny yellow sections there essentially represent what you see on the left on that photograph. And I'm afraid I've run out of time completely, have I? In terms of the media interest, I suppose this is the most interesting bit. I am sure there are real experts on the issue, much better place to talk about it than I am. So I'll just give you a brief rundown of this. The deep storage site is considered to be the main alternative to a surface storage sites, and it is considered to be technically viable. There are already licensing processes underway and completed in Finland and in Sweden, and there's a very strong international development and research community for these deep storage sites. So there are two alternatives. Deep storage, which is probably not the final, can be considered the final solution, or another solution that is still not waste-free technology, waste-free process. The deep storage site will be processed and will be operated by the Czech government. The main principles are obvious: safe storage. The storage site will be located about 500 meters below the ground in safe material, safe mineral environment. And obviously this is subject to strict procedures by the ministry and the regulatory authority.
So the time schedule, the timeline for the selection of the location for the deep storage site, which is valid at this moment, includes the time since the period since 1997 till roughly 2030. In 2030, we expect the location for the deep storage site to be selected, as well as the backup location. And then we should conduct the construction and operations of a confirmation lab in the selected location. That will be the base for the future deep storage site, and optimization of the storage site will be also done in the period of 2030 to 2035. Then the licensing process will start in 2035, and we expect the construction of the deep storage site in the period of 2050 to 2065, and after 2065, the storage site should be operated. The current state of affairs, out of 9 locations that we had in December 2020, the government selected 4 locations: Březový potok, Horka, Hradek, and Janoch. So that's as much as the deep storage site goes. And this slide is about research and development in Surao. And we can split it into 3 areas. First of all, research and development in the process of preparing the deep storage site, and research and development for safe operations of the existing storage sites. And the third specific group of activities, that's research and development for the elimination of radioactive waste, which does not come from radioactive or nuclear activities in the nuclear power plants. So when it comes to other activities of Surao, we have underground research center in Bukov that was based on or built on the basis of a project that we ourselves initiated. It's in a historical mining site called Rožna, where we excavated uranium, and we have turned it into a research center. So at Bukov Research Center, we also expect to have international cooperation projects in the framework of the international community, which deals with research and development related to deep repositories or storage sites. The depth is roughly 550 meters, which is the same depth as the deep storage site should have. So we're researching things like underground water, changes in building of deep storage sites, and we conduct various experiments relating to the construction of the storage site. So that was my last slide. Thank you for your attention. If you have any questions, I'll do my best to answer. Thank you, Mr. Sud. Do we have a question? Well, I would like to know whether the authority of the radioactive waste also administers the desludging location of uranium ores. That's a location which was in South Moravia by Midlovary. And also we have another location. Does that fall under your administration? Well, these locations are classified as locations that conduct activities related to radioactive waste or radioactive ores. So that falls under Dynamo's activities. So it is not our activity. So any waste relating to the mining of uranium ores, they're not considered to be radioactive waste, even though they contain radioactive materials, but it is not a radioactive waste that we in our authority are responsible for. So the desludging locations conduct activities that are related to what we do, but it does not fall under our administration. Next question. Well, I have a question. We met many times at various discussions about the burnt nuclear fuel. When is the burnt fuel transformed into a nuclear waste? So when we talked with Czech, Czech is responsible for the operating, you're responsible for the storage of the nuclear waste. But who is responsible for saying that something is nuclear waste? Well, we discussed it in Surao, in our authority ourselves, and we're not clear on that, but we had some legal opinions conducted on that, and it is not so simple. The previous Nuclear Act from 1987 stipulated that the radioactive material, which cannot be further used, the owner could declare it to be radioactive waste or nuclear waste. We did not find any such definition in the current Nuclear Act, and our lawyers are not clear on when that moment happens, when it happens, and who declares the material to be nuclear waste. I know that it is a hot topic also in relation to some imports of materials from Russia. So I just can say that in terms of legal framework, it has not been clear enough. Well, we have to speed up, and it's your role to stick to the time schedule. Okay. And the next speaker is Mr. Václav Svoboda from Škoda, and he's used to work fast and speak fast. So his presentation is called a storage files at the burnt nuclear fuel. Well, in my presentation, I will talk about the fuel components, or rather containments that we now deliver to Dukovany and Temelin for storage of of burnt fuel. So that's one of the main activities that we do. We manufacture containers for the burnt nuclear fuel and also for the storage and handling of various nuclear components. On the left-hand side, these are containers for the storage of fuel. And then in the middle of that slide, you can see metal container for various radiation sources. And on the right-hand side, you have large containers, 120 tons, that we delivered to Ignalina and Chernobyl. But I'll mainly talk about these two blue beauties, containers, Škoda 1000/19 to store 19 pieces of fuel from VVER 1000, and on the right-hand side, Škoda 440 to store 84 fuel cassettes from the VVER 440 reactor.
The 1000 series is for the Temelín, and the 440 is for the Dukovany nuclear power plants, these two beauties in blue. Very similar structures, it's just different size and different type of the basket for the fuel, spent fuel. Two forgings welded together. These are from steel, and these are 450 millimeter thickness polyethylene shielding, plus the internal shaft for the fuel is covered with sealed lids on the bottom and on the top. And these are several tons of forgings with corrosion-resistant steel. It's a lid. In one case, it is welded. The other one is screwed upon. And then there is a protective plate. And for handling these, there are the sections and pins for attaching whatever you need to attach in order to handle these. And also there are cooling elements on the surface. Škoda 1000/19, some technical data, 5.6 meters high, the diameter being about 2.3 meters. When it's empty, let me check to get you the precise figure. It weighs less than 105 tons, and if there's filled up with 19 fuel cells, it's almost 120 tons. If you add the suspenders, then it's almost 137 tons. And this is the technical data sheet for the Škoda 440/84 container. It's 4.7 high, the diameter being slightly over 2.7 meters, but almost the same weight as the previous type. In its empty state, it's 102 tons. If you add 84 fuel cells, it's over 120 tons. And if you add the suspension system, it's 138 tons altogether. As regards the container system for spent fuel, the Czech nuclear legislation stipulates that this is special safety or security equipment class 2. There is a special decree number 379, and these transport systems are intended for fissile radioactive material. In other words, this is the kind of device that really needs to comply with the strictest of requirements in terms of its being able to handle nuclear accidents. This is the SSR6 of the International Atomic Energy Agency. And these are structural tests. These are other tests and requirements for licensing and also requirements in terms of transport, all of that, this is stipulated by that requirement, by that precision, by that prescribed document. But that's the end of it. In light of that, we had to do our own homework in terms of what kind of material would you use, what would be the tensile strength, what kind of handling pins would be used, etc., etc. These transport containers also comply with ADR and RIV, which are essentially prescribing the standards for safe, secure transport by road and rail. And the Czech regulatory authority prescribed in decree number 358 of 2016, also the documentation requirements, the requirement for independent supervisors during testing, etc., etc. A lot of paperwork. A couple of the main requirements in terms of the structure. Minus 40 degrees Celsius is the level that they need to handle in terms of the lowest temperature. Mechanical capability or withstand capability is 9 meters from absolutely, well, absolutely, what means absolutely? Nothing is absolutely solid, but it's a very, very conservative specification, I would say. And also they need to be able to withhold and withstand a fall from 1 meter to a steel pin with a diameter of 20 centimeters. Also, these containers need to withstand the pressure of water of 200 meters deep. There's no way you could do this in Europe. They need to withstand 800 degrees Celsius fire for 30 minutes during transport, and also if a small plane like the Cessna Piper, for instance, goes and hits this container at about 80 meters per second, it must still withstand, the container still must withstand that impact. And also the 0.1 millisievert must be the level of radiation that is leaking in special conditions. The transport containers had to be compatible with the already supplied and used and established equipment of power plants, such as the equipment, the feeding machines, the shafts in the pools, handling corridors, transport carriages, etc., etc. A couple of interesting points from the development and manufacturing stage of this, and I'll specifically be talking about the Skoda 1000/19, because that was the first one that sort of paved the way for the subsequent Skoda 440/84, because we used analogical procedures, materials, etc., etc. The exception being the basket for handling the fuel cells, because it was part of the Castor 440/84 for the EDU in Dukovany. We started to develop these in 2012, and the first one was supplied in 2018. So it was 6 years from design to delivery. The first transport system 440 was developed then delivered in 2021. 58 of these Skoda 1000 were supplied to the ETE, and 33 pieces of the 44 unit were supplied to the Dukovany site. During the development stage, we had to check various sorts of materials so that our people could calculate the material characteristics, the bodies, the suspensions, and the crash zones, etc., etc., with various temperatures, various environments. We also tested the internal shafts in dry conditions, in the boric acid. We also tried various materials, particularly mechanical properties of these and the impact resistance properties of these materials, etc., etc. I'd like to say that the first 5 1000 series units has a fully metallic structure with aluminium and containing also boron, but unfortunately the supply was so unreliable that we've decided to develop our own system that is made of stainless steel pipe that is welded together with content of boron. You'll be able to see this in the images. And also did deep boring system and testing. You will see that. And it'll be a lot of special equipment that we had to produce in order to do this. We also tested new methods such as Toft and phased array for defectoscopy, non-destructive testing. And one particular development that was particularly interesting, that was the aluminium-based piping with the content of boron. It was only number 56 of the option that everybody involved was happy with the outcomes, the tensile strength calculations and the subcritical mechanical properties, etc., etc. It took a lot of time.
So for the containment, Škoda 1019 and also Škoda 440/84, we delivered some 70 different accessories. In the first half of 2018, we've conducted functional tests in Škoda of the first container with all the accessories, and we simulated a real run or real operations at a power plant. So we filled the container with water, we tried out drying and so forth. Then at the end of 2018, we delivered the first container to Temelin, and then in 2019, we conducted tests at both blocks of Temelin power plant. So we tried to apply the container in practice, put it or loaded it with fuel cells. First, we started with mock-ups and then active fuel cells, and we also tested on a repository of burnt out fuel. We already finished the functional trials for Škoda 440/84, and then as of October, we will conduct similar active and non-active trials in Dukovany power plant. So to achieve an approval of the given type of container, we had to put together an extensive file of documentation and drawings. So we had 21 calculation reports, various subcritical calculations, resilience of various types, and so forth. 17 detailed material specifications, 40 drawings, 29 guidelines and manuals. And altogether, it amounted to some 4,000 pages, A4 pages of text. So before the state authority for nuclear safety issued its approval, it took 1 year. So for the manufacturing of the container, we created 140 pieces of drawings, production drawings, sizes of A4 to A0. We had 200 various technological facilities and 3 special sites. The trials of Škoda 1000/19 took 6 months. The first Škoda 1000/19 was tested for almost 2 months in Temelin. and Temelin and the bent fuel repository, and Škoda 440/84 container was tested for 2.5 months only, because the process was analogical. We had the same lids, the same bolts, so we could speed up the process. And these are a few photos from various activities that we conducted with the containers. Welding of the containers. We had a special welding site opened for that. It's a welding robot. The welding head was qualified and tested and functional up to 550 millimeters. It's a unique site in Europe. We're not aware of any other site of that kind in Europe, anywhere in Europe. So you can see the welding robot in ESAP, and the other pictures show our own welding site in the reactor hall, which is nearby this university. We also needed a deep drilling machine to drill openings for polyethylene rods. The rods are used to shield off neutrons. There are 2 drills of diameter 97 millimeters, and the lengths of the drills 4,460 millimeters and 4,610 millimeters. We were concerned, or the biggest concern was that roughly in the bottom third of the drilling, we would not be able to hold the line. It actually happened during the trials, so it took 10 more months to fine-tune the drilling head to drill the opening as we wanted it. This is the manufacturing of the welded pipes from stainless barium and the assembly of the basket. The welding was done at a special welding site, and the pipe is always put together or assembled or welded together from 6 pieces. So this is an assembly process of the basket, and the assembled basket on the right-hand side. These are a few photos from the trials of the first container in Škoda. So we tried out the whole cycle. So we added water to the container. We tested the insulation. We drained out the water. We tried to put on the transport suspension system and so forth. The trials took over 6 months, and we conducted various modifications so that everything fits in perfectly. So these are a few photos from the Temelin power plant. We had to test the container in Temelin as well. So we have photos from the burnt fuel storage site. We had to test out various handling steps and transportation on a transportation wagon. We were quite concerned whether we will be managed to drive through, because we know that our colleagues that delivered a container of the Castor type did not fit in the opening. So when we were in the opening, there were only 2 centimeters left between the top of the container and the ceiling. So we were sweating quite hard. You can see the container and the additional fittings and accessories. And we had to try it all out so that we do not damage the bottom. We tested out all handling steps. And on the last slides, you can see the container filled in with 19 pieces of fuel cells. And on the last photo, the large one, you can see the positioning of the primary lid, which is done underwater. You can also see the trials of the first container of 440/84 here in Škoda JS. We did similar trials as with the 1000 type, so we put it on the transport train, all the fittings and accessories being put on, helium tests of the seals and so forth. And since October this year, we will do all the whole series of trials on site in Dukovany, on both blocks of the Dukovany power plant. So that's all on my side. Thank you. I guess that discussion will have to take place during lunch or coffee. So let's agree that discussion will be done afterwards in the foyer. So let me give the floor to the last speaker, which is Michal Mikulášek from Škoda JS, and he will talk about the dismantling of the steam generators at V1 Jaslovské Bohunice power plant.
All right, can you hear me? All right. Good afternoon. I'm Michal Mikulášek, and I'm the designer in the technical preparation of projects in Škoda JS, on that department. And I'll try to share with you the presentation on decommissioning, on our part of decommissioning at V1. I will first speak about two projects that were in the phase of offers or proposals for Ringhals, and then I'll be talking about the Jaslovské Bohunice V1 unit, where we were involved with the transport and dismantling of the in-containment and the pressurized vessel. Ringhals is located in southern Sweden, about 50 kilometers south of Göteborg. And at this moment, they decommissioned two reactors. The first one is a boiling reactor. The second one is the Westinghouse type of pressure water reactor. We prepared the technical solution for the pre-project phase, i.e. handling heavy cylindrical objects, positioning heavy components for cutting, protecting the bottom of the pool against falling of heavy objects, shielding the staff there, plus covering the vessels of the reactors. We designed this fixture, which would hold the heavy components. Then it would place the components on this desk, and the cutting would be happening 10 meters below the level of water. That figure there is just to show you the size of it. It's probably interesting for you to look at the pins on the left side of this picture. These pins were there originally to provide water flowing under the device. Then there would be some shielding components. This is a shield on the left for one person. On the other side, you can see a tower that'll be about 10 meters below water, and there'll be a person inside to control the cutting process. And the solution would include a lid for both the pressure water reactor, that's one on the right. The left one is much wider, much thicker. The segments are there so that you can easily transport and handle these pieces of equipment and these fixtures. Another project included a fixture for the Philipsburg power plant, usually dry and cold cutting. It's orbital cutting from the outside, and then you transport the cut pieces, the fragmented pieces, out from the reactor vessel. Another project was in Biblis, Germany. You needed to remove the pieces that stick out through the biological containment, biological protection zone. So you would fragment the reactor. Again, we proposed orbital cutting from the outside. I suppose it's a Westinghouse make of reactor. Now, over to Jaslovské Bohonice. I will talk in more detail about this. You know where the Jaslovské Bohonice power plant is located now. This is in Slovakia. And my colleague from Javis told you a very nice detail about the decommissioning process. And I will tell you more about the transport of the heavy components fragmented. The Jaslovské Bohonice nuclear power plant uses the VVER-44 Type 230 reactor. It's known as the double unit. Most of them were used in former Eastern Germany. The ones we use here in the Czech Republic are Type 213 rather than 230. The difference is in the cupola, the yellow sections there. And the size of the yellow marked yellow units would be much smaller in the 2213 type. The first block was in operation until 2006, the other one until 2008. The decommissioning process started in 2018. And as regards the transport of the in-containment parts and the pressurized cylinder pressurized vessel, I can say that the in-containment parts are relatively easy to handle because you simply operate just as you would in the operating environment of the live nuclear power plant. Some of these sections you can see here are not fragmented yet. So there were pools for underwater wet cutting. And this is a list of the individual sections to be transported. And the first block would be removed, fragmented, then moved over somewhere, placed somewhere. It was quite some work in terms of planning. As regards the transport of the pressurized vessel, we provided a lot of fixtures and equipment to handle the whole project. The beam, the cross beam, needed to be made again, although there was one originally when they constructed the power plant. That's the greenish section there, the greenish element. We just had to make sure that the cross beam fits into the place available there. And then there were caps placed towards at the end, so that we could work in the planned manner. The process of removing the pressurized vessel, we first had to remove the cap and the valve section. Then we placed the crossbeam into the pressurized vessel. There was no corrosion, no problem. They had a problem of that sort in Spain because it got kind of stuck due to corrosion, but we didn't have any problem of that sort. You then simply lift up the pressurized vessel, the pressure vessel, and put it elsewhere, and then you do the rest of the job. These are the transport routes for the reactor into the cutting pool. What might be of interest is that the reactor is quite long, and the height above ground was very, very small. So everything had to be really fine-tuned, and everything had to be done very accurately. There were 12 pieces altogether of the pressurized, of the steam generator, that had to be removed from the plant room. Theoretically, you could use the short route, but unfortunately we couldn't do it because of certain structural elements like bridges, etc., etc. So we had to go all around the plant. Section or room 490 is the plant room. This is where we had to go with that steam generator. The steam generator is 12 by 3.5 meters. The design weight was 160 tons. I could only see 145 tons in reality. Now, this is the type of location. This is the standard for 4D reactor. That's 6 steam generators all around the reactor shaft and the reactor. And this is what the steam generator looks like when you model it at the VVER 440 type 213. That's the one we have in Mochovce. A lot of piping, a lot of platforms, a lot of air technology, and all of that needs to be removed so that you can remove the steam generator.
The dismantling was done simultaneously on various steam generators. We had to release the caps of the pipes, and then remove the supports that the steam generator was resting on, and it was connected to that support through a suspension system, and then we lifted and released the steam generator into its position at the bottom. So then after we lifted the steam generators, and it was actually done into parts. The 3 steam generators are the blue parts, and the manipulation opening is 12 times or 9 times 4 meters. The steam generator is 12 meters on 3.5 meters. So we had to lift it reclined with the angle of 40 degrees. So the ropes once fixed on the steam generator did not move anymore. So we had to fix the ropes on the steam generator properly for the first time. And the angle could have been slightly different every time. We simply had to manipulate or handle the crane so that the steam generator fits in that smaller opening. So we had only 3 openings to get the steam generators out, because we simply could not create a bigger opening in the ceiling. We put in place a special rail and special undercarriages on which we placed the steam generator. So as far as I'm informed, the transport of the steam generator from its original location under the opening took some 25 minutes. So when everything was ready, the transport itself didn't take so much time. So once we lifted the steam generator through the opening, we had to transport it into the corridor. The steam generator was kept reclined on the crane. The ceiling is quite low, so the steam generator just about fit in. Plus, there were other materials as a result of decommissioning, so we always had to clean out the transportation route and then transport the steam generator into the corridor. Then in the corridor, we loaded the steam generator on a load truck, on an undercarriage, as you can see on the picture, and that carriage was remotely controlled, and thanks to that carriage, we were able to take it out of the block. The seals were only 5 millimeters from the bottom, that is from that undercarriage, and the design hired is 50 millimeters between the gate and the seal of the collector. I was there when the first steam generator was transported, and that was a success. So I suppose the others were successfully transported as well. So this is the transportation route. What was interesting was that the truck had to go through a number of gates, and the remotely controlled truck works really well. The whole journey took some 45 minutes, and it was done by an Austrian company, a very professional company. I don't recall the name. So when we put it on that truck, they simply transported the steam generator to the plant room and without any problems. So that was the project design for the transport, and this is the final location in the plant room. So when lifting it and positioning it in the plant room, we also had to put in place a cutting location. The cutting of the steam generator was already described in one of the previous presentations. So we managed to transport all 12 steam generators in the given time. And that means we complied with one of the major milestones for decommissioning of Jaslovské Bohunice B1 nuclear power plant. I tried to speed up so that you have time for lunch. Thank you. So thank you, Mr. Mikulášek, for a very interesting presentation. It was interesting also for all of us from Škoda, because not all of us were there when it was happening. So I guess I will hear now that I did not manage the time properly. Well, the problem is that there's one more session in front of us, and we're already officially at the end of the break. So do we have Mr. Kolovratník here? No, he's outside. So are you willing to postpone the last session? Well, let's have a 15-minute break. The last coffee. Well, actually, we should have lunch now. Well, that's great. So I'll speak to Professor Kolovratník. So let's have at least 25-minute break for lunch. So thanks to the chairman. Thanks for inviting me.
Disciplinované množstvo.
Tak dobrý den, dámy a pánové. Dovolte mi,
Good afternoon, ladies and gentlemen. Welcome to session 5. We'll be talking about turbines for nuclear power plants and heat for district heating system. Professor Kolovratník will be our first speaker. You have the floor. Thank you. Dear colleagues, let me open this session by sharing this presentation on turbines for nuclear technology, which I've written together with my colleague, Mr. Dostal, a well-known name in the business. It's pretty obvious, essentially, that we all need electricity. About 90% of population of this planet have access to electricity. We essentially know how we get electricity. It's direct or indirect transfer or change from a source, be it steam or gas, or etc., etc. So you get heat, and then you convert it to work, electrical work, and usually you change this electrical work into electricity. And based on the heat exchange systems, it's either steam or gas cycle. There's an expansion system. Usually this is a turbine type of machine, can be either steam or gas. The expansion part will be my responsibility, and the second part will be covered by my colleague, Mr. Dostal. So talking about steam turbines, we know that we'll have 140 years of experience, practical experience, pretty soon. So when the first nuclear power plants were installed, they already had 70 years of experience available to them in terms of steam turbines. And there are a couple of non-unit facilities that we can have, non-unit equipment that we can have, and a couple of things that come to play. That is the output, the phenomenon of wet steam, and new opportunities that I see in the area of these technologies in relation to nuclear power plants. As regards the output, the installed capacity, despite the reduction in the number of nuclear power plants being built, all the individual units have gone up tremendously, from single units of megawatts up to lower gigawatts currently offered or being installed and already operated as well. We know it's over 50 units of nuclear power plants, the oldest ones from the 1980s, Mochovce, near the Slovak border, the border with Slovakia, and the electrical output being 1 gigawatt, and over that, over 80% of the nuclear power plants abroad have that level of output. There's 442 stationary electrical nuclear power plants with roughly 500, shall we say, almost 400 gigawatt electrical of installed capacity. So the first issue I wanted to address is that of the installed capacity or output. And you know that the steam turbine, together coupled with the nuclear power reactor, is the most powerful stationary motor that is available on this planet so far. If you looked at the last year's conference proceedings, you know that Mr. Zobek has already provided a very in-depth account of these things. So just to recap on the basics, if it's 50 hertz, full RPMs, it's over 1 gigawatt. If it's 25 hertz, 1/2 RPM, There are units being built with installed capacity of 1.7 gigawatt, and we are going closer to the magical border, magical limit of 2 gigawatts. When I was a young boy, it was a hypothetical limit. Now we're in a situation where we could actually get an installed capacity of 2 gigawatts per unit. There's quality and quantity. The quantity is the flow through of the media through the system. The quantity is then the quality is then the electricity that we can get out of this. But it's interesting to see that these heat motors are available for many companies, and it's interesting to see that it's not the syndrome, how we would say, of a pattern being copied over from the one nuclear power plant to another, for instance, like Concorde and Tupolev in airplanes. It's like being twins, single-egg twins. No longer the case. You can look at this as a configuration that could be seen as a combined single flow, high pressure, low pressure unit, plus 3 two-flow units for the biggest units. If you look at another approach, let's say company S, seeing 2-flow high pressure and 3 low pressure, high pressure units, we are getting closer to 2 meters of the length of the blades for the turbine. So it's 75 inches. The other producer offering something slightly shorter. And it's interesting to see that we are getting closer to the configuration that we know from Temelín, the high pressure section having a lower output, and the low pressure section then combines this up. It's the 40 to 60. Some other manufacturers say it's 60 to 40, but it's quite interesting to look at this, unless that's a mistake or an error. We know that a Chinese nuclear power plant in 2019 of the first unit in the UAE, and of course it's the full RPM blocks that are units that are being actually installed and commissioned at the moment. And it's not just company A or company S or type A, type S, as there's other sorts of technologies available. Generally speaking, though, in order to cover the electricity or power demand for the humanity, is at 600 exajoule per year. If that was to be represented by this pie chart, then this section of it, 30 to 40%, shall we say, is then converted to electricity using various mechanisms. And of that part, the dominant part of that would be converted using steam turbines, either conventional or coupled with nuclear power plants or some other technologies. So the steam technology, steam turbines, is the prevailing technology used at the moment, and is very significant in terms of the statistics. And of course, this is related to steam turbines, not just the steam technology in general. And if you look at the economy of primary resources, we need to talk about efficiency, reliability, flexibility, and life expectancy of the steam turbines proper, as well as the auxiliary systems. In practice, we know that the majority part of the facilities work with relatively low characteristics, low capacities steam, low specifications of the steam, if you compare it with the traditional. If you look at the expansion, thank you. You can see that we are seeing a prevailing dominance of wet steam cycles. And in order to assure reliable turbines, we should handle very well technically the two-phase flowing of wet steam in that wet section. And it's something that I've been interested in professionally over a long period of time. And I did look at the proceedings from the last year's conference. And again, we have an excellent presentation there from the last year's proceedings on wet steam. So in the flow type of the turbine, it's two-phase flow, either from superheating and then interacting with the flow-through section. There are two impacts at two levels.
So there are additional energy losses that can decrease the natural efficiency of the machine by a few percentage points. And then when the water films fall apart, you can have a rough dispersion, be it a nuclear or non-nuclear machine or a device. It will have potentially an impact on the losses, erosion or corrosion. So in this respect, our research site cooperates theoretically and experimentally with Škoda Power, and there must be a necessary knowledge of mechanisms of the inception and development of the steam phase and how the steam phase develops and interacts. So because of the lack of time, I will be brief. In the real steam turbines, thanks to the fact that Škoda Power prepared the instrumentation, we're able to measure the development of the steam stage, both in the axial direction and the radial direction, and around the device. In the circumference direction. So this is an example of a commercial software output, and thanks to the experiment, we can verify that or fine-tune it. And we have certain design regimes and non-design regimes that we simulate in cooperation with the manufacturers. So this is, for example, an interaction of instrumentation in the jet field and the influence on jet fields. New opportunities for turbines in nuclear technologies. If we're active in the energy sector, we are aware of the fact that energy is at a crossroads. It's not that we do not have sufficient tools or technologies to successfully get through that crossroads, but we're in a situation when quickly changing and migrating policy of road signs makes highways into dead-end roads, and we're scared to even start the project because we don't know whether anybody will continue or finish those projects. So we're in a completely new situation. So if we're able to cope with the ambivalent nature of the coexistence of mankind and nuclear energy, we can say that there are new opportunities. The substitution of fossil energy, fossil fuels, then of course the modular reactors. That also offers certain space for turbines. And if we select any project to use nuclear reactors of the fourth generation, that is an opportunity. And nuclear fusion, that's something that we've been waiting for the past 80 years. It will need a thermal circulation, a thermal circuit as well. So to close down that part, I can say that nuclear technologies, from my perspective, at this moment, co-guarantee the future of turbines. It doesn't have to be only steam turbines, and we can document that in the second half of our presentation that will be presented by Mr. Dostal, who will show us one possible example of using gas turbines. Thank you. So thanks for giving me the floor. So let's talk about different technologies than the traditional steam turbines technologies. The steam turbines as a technology have been fine-tuned to the maximum, so there aren't many open crevices, any more opportunities. So at this moment, we're in a situation when we simply have the light water reactors, and we always make fun of it, that the young engineers always need to produce the best and most modern reactor, and they discuss it so long that at the end they have a water pressure reactor, just yet one more water pressure reactor. So light water reactors, they are here with us, and then nuclear turbines will continue playing a key role. But there are many new projects that we've heard about. And on those projects, we can apply different thermal circulation systems, and we've been researching them in our institute for the past 20 years. It's nothing new. So you can see that we can try to catch up with the fusion quite well, and we're working on the development of the nuclear fusion. The advanced reactors and reactors of the fourth generation account with higher operating temperatures, so there is not much, doesn't give much space to steam. The operating temperatures can be up to 1,000 degrees of Celsius according to design, and it's just a question of finding the proper material. So steam circulation is not the proper way to go, because that would limit us when it comes to temperature. The high temperatures would not make sense if we apply steam circulation. So steam circulation would not be so attractive, and it would be good to look at other alternatives. And one standard alternative that's been researched to are various closed Brayton or gas circuits for nuclear energy. They're researched into together with helium, because in the beginning there were many scientists or physicists that were involved in that research. As a technical gas, it is not so good, because anybody who operated a helium circuit would know that it's very difficult to develop devices for that. Helium is expensive. The leakages of the helium cause problems. So it is not as simple as it seemed in the past, that helium would be a primary circuit gas for advanced nuclear blocks. And to have an attractive efficiency, we have to reach temperatures of roughly 800 degrees of Celsius, which is a relatively high temperature. The technology has not been tested, and also there's a big question mark when it comes to regulation of the closed circuits and a compensation of the volume changes. And since it's a gas circuit, gas circulation, it is rather complicated to do this, because the volume of the compensation vessels would have to be huge. We're coming out with huge numbers. So then it's a question whether the economy and the compactness of the gas circuits is reachable, is achievable. So that is when the thermal circuits with above critical CO2 step in to play a role, because they have a number of advantages in comparison with helium. First of all, we can achieve higher efficiency than the ideal gases, because it uses real features of the above critical CO2. The critical point, 1.3 degrees of Celsius and 31 megapascals, 7.5 megapascals, sorry. And we know how to calculate the efficiency of the turbine. So whenever you decrease the output of the compressor, you decrease the efficiency of the circuit. So on this picture, you can see the calculations of compression work performed. So if it's an ideal circulation, ideal circuit, if you can see the laser pointer, before we reach the critical pressure, and this is the pressure ratio, the curve is similar to the ideal gas. So in case of ideal gas, no matter what pressure we have, the work performed would be the same. And the whole area would be a part of one curve. With CO2, if we compress at this point, and this is for 32 degrees Celsius as an input temperature into the compressor, in this area, the compression work goes significantly down, and that's what the thermal circulation plays with, and you can play with it for a long time.
And that will dictate what circuitry you will decide to go for. There's one more factor at play in this context. If we use the CO2 with the benefit of the compression work, the real life properties of that gas will cause it, with the different temperatures and different pressures, although it being one and the same gas, the properties will be completely different. So in the regeneration heat exchanger, we have the standard delta T with ideal gases. The delta T will have changed with CO2. And there'll be what is known as the pinch point in the heat exchanger. That is the temperature gradient is the lowest there, as you can see that, the pinch point location, the value there of that curve. And you can't then simply set a delta T that will happen throughout that compressor, throughout that compression work system. But it'll be different then. And you need to play around with it, and it makes things much more complex, much more complicated. This is a study by Professor Jelin from the 1960s. He was very involved, very heavily involved in this. And we have this this type of compression circuit, and this is a recompression circuit. This is a recompression circuit with divided compression after the cooler and before the cooler, and the enhanced regeneration is a 3-valve heat exchanger. So there's a whole lot of options that you can test and you can use for various applications in a host of manners, because you can play with the input parameters, particularly how you put the heat into it. The most frequent variant being the recompression circuit. It's pretty frequent because it's very suitable for the advanced reactors, such as Generation 4 reactors, or research reactors that never really made it to Generation 4, but still are used in research. So in order for the pinch point to happen in that heat exchanger, we use divided compression. There are 2 compressors running in parallel next to each other. And we want to prevent the recuperator with the lower temperature to drop to the pinch point. This is the full flow, but between 2 and 3, it's only that part that has not been recompressed from 8 to 3. So that's what's happening between 2 and 3, these 2 points. And that allows us to reach a higher level of efficiency for the whole circuitry, which means that if we have sources of energy that are not located between 4 and 5, which is traditionally a reactor, I'm sorry about this, here we are. And if you have something that is closer to the thermonuclear fusion, as has been mentioned, or for instance, use of waste heat, then you bring various sources of heats there, and not only here, but also on the way to this point. And in that case, it's not a recompression circuit, it's other types of circuits. And you can play around the optimization with this. It can take years for you to tweak these for individual applications. And it's a fairly interesting type of research and very interesting topic of research for various different applications. Just to recap on the efficiency I've mentioned. The supercritical CO2 is good for temperatures above 500 degrees Celsius, which is where it intersects with the traditional cycle. And at the same time, it reaches higher levels of efficiency than helium. And the question is how things would play out if we reach a temperature of 900 degrees Celsius, for instance. But helium would probably work, but I'm saying probably because this is not commercially tested yet. And the question is what the parameters actually would be with these high values. We know that some British reactors are operated up until up to 700 degrees Celsius and no problem. But you can see that even with the temperatures at around 500 degrees Celsius, the CO2 system is not way beyond the efficiency levels of the traditional steam cycle. It's the compatibility of the equipment that is at stake. The steam cycle is well known, is optimized, and also in terms of efficiency is really it is really well established and it's doing well. So it's a tough competitor if you think of it in terms of the type of cycle to be used in nuclear power plants. I've been working in this field for about 20 years and even longer in our department. Our department has been dealing with this specific topic for much longer than that. And if you look at the parameters of the turbines and to be replaced with CO2 cycle, you need to take into account that there are high temperatures between the points 4 and 5. So it's not quite, the CO2 cycle would not be that suitable for fossil fuels. Generally, when I did my doctoral study on this topic, the prevailing opinion was that this type of cycle would be suitable for nuclear power plants. It's irony, it's that the demonstration unit is the Alamo cycle that is on fossil fuel in Texas. And it's going to be probably one of the first experiences with the supercritical CO2 cycle. Although it is not exactly the type of a cycle we're talking about here. But we'll see about the synergy, and if it was to play out well, then the synergy would be huge. And we also talked about the advanced reactors, lead and bismuth type of reactors, and also sodium reactors. But then we found out that CO2 also oxidizes sodium, although smaller, in a slower manner. And with CO2, the leakages are more difficult to detect rather than steam, which is basically acoustic-based. So as far as I know, sodium is being departed from. And then the various reactors, we talked about at least 300 megawatts, and it's difficult to imagine that we would start off in a demonstration project with a 300 megawatt reactor. So it's more reasonable to start with something smaller. So it was the waste heat systems and also solar power plants, etc., etc. One of the units that is built in the United States with the support of DOE, they are going to have a system for CO2 cycle. And the next thing we do with the University of Leipzig is accumulation for caves, and that's a hot topic as well, and compression of air into caves is interesting and well established, although it's got some disadvantages. And the last thing we do would be fusion power plants. The CO2 cycle would be interesting for two reasons in this context. One, the steam cycle is not that good, because if it were to hit the vacuum chamber of the big reactor, it would essentially mean the destruction. So it's been always considered the best policy to think about the helium cycle. And we're also talking about the supercritical CO2 cycle, and we're based in our considerations in the philosophy that the heat is brought with the high energy neutrons. It's all around available there. You have heat flows from all sorts of units and pieces of equipment, and CO2 would be great for that, because you can connect it easily and you can employ these various ways to harness the sources of heat into the heat circuit proper.
So you can build a special cycle, which is tailor-made for the given power plant. So the specifics of designing the rotation machines or devices, there are various challenges. So I'll start with this slide, why we do it. The turbines for CO2 are very small in comparison with other turbines, but of course that brings along a multitude of problems. It looks nice because it's compact, but then we have a problem with the length of blades. So if we go to lower outputs, up to 10 megawatts, then the blades would be millimeters long, just a few millimeters. So you cannot have a small axial turbine for CO2. So that slows down the development, because you have to go into large outputs, and nobody wants to do that. And for small machines up to 10 megawatts, we will have to have a radial solution. So, and that's a big machine in comparison with the axial machines. So then we try to increase the revolutions per second, and that causes additional problems, because then you have to synchronize it within the network. So that's another problem. And then, of course, you have a high output per blade, and that means that the whole machine must be really resistant and robust. So there's a lot of space for research, and it's going to be a long run, and maybe not such a long run as with the light water. Lubrication, that's another problem. CO2 dilutes standard oils. It might seem to be a small problem, but it's a problem you have to solve. Ball bearings, large axial powers, that's a problem as well. Seals, the labyrinth seals do not work because you have a high critical weight flow. So there's a big loss, a huge loss. Then you have contact seals, but then again, there's a problem with pressure. And my conclusion is that the efficiency of CO2 cycle is not significantly higher than the steam cycle. The compactness, that's the biggest advantage, the key advantage. We have complications with designing small units, and a significant advantage would be only if we go into higher outputs. So we have to be flexible and to research into a wide spectrum of applications. And then as we get to know the technology, we'll be able to apply it at a wide spectrum of various heat machines, heat devices. Thank you. So before I say thank you, we have time for a few questions. Do we have questions? So it's just a comment. As old, I'm so old that I saw Třinecké iron works and I saw a radial steam turbine. And it was an interesting solution. You talked about radial turbines, but of course the development went towards axial turbines. And back then, in those times, I think it was Stahl Laval who invented a turbine without a stator, without the static part. So those were two rotating parts going against each other. And then there was a generator rotating in the other direction. So maybe that's an alternative that could be researched into. Well, yeah, there are many other alternatives that we can have a look at. The device without the static part, and the blades go against each other, rotate against each other. So, and the generators again rotate against each other. We cannot hear the gentleman without the microphone.
Pane profesore, já vám na mikrofon, že se to překládá a oni by vás překladatelé neslyšeli.
To je jenom drobný koment k tomu, co říkáte.
So just a short comment on what you're saying. The radial turbines are commonly applied in other types of applications. So they're still here with us. So we have turbines in the field of micro turbines. And when it comes to the rotating blades that go against each other, the Lindström system, that's something that was built, and there's documentation for it. Siemens researched it in great detail, but we don't see it as an ideal way to go, a route to follow in energy, in the energy sector. So it's not an interesting concept for us. Any further questions? So thank you, gentlemen. And the next speech will be by Mr. Prchlík, Dosan Škoda Power. Dosan Škoda Power in nuclear power plant projects. Okay, so I'll speak to the microphone so that I can move around. So good afternoon. The presentations were excellent. We went through the theory, and it is interesting. We also deal with CO2 turbine, and the chart when it showed the efficiency around 450 to 550 degrees of Celsius, and the efficiency was roughly the same. It didn't much differ from the steam turbines. So I could see that thermal flow did not make a mistake. It was a disappointment for me because I expected a higher efficiency, but I understood that our colleagues working with the CO2 target a much higher temperature than we have in steam turbines, and multiples of the temperatures that we have in pressurized water reactors. So, as we've seen, or as we've heard, 70-70. In Škoda, it was 100 years or 120 years, but I think we kept in touch with the competitors. We are one of a few manufacturers of steam turbines that are still on the market. We are a part of the Dosan group, Dosan Holding, and we're doing well. We manufacture not only steam turbines, but also everything else around it. So, as we've heard, so far, we can have various sources of energy to tap into. And you can see on the market that investments flow into large power plants, but apart from that, they flow mainly to the process area where steam does the work. for example, in steel works, in paper industry, paper manufacturing and processing. And there are also applications in renewable energy or semi-renewable energy, for example, burning biomass or using waste as a source of energy, so waste to energy. So we are the world leader when it comes to the volume of deliveries in this area. So I can only sum up what I've already said: the steam turbine design and the construction, manufacturing here in Pilsen. We also have the capabilities needed to do after service outside of our manufacturing plant. But of course, we have to have a properly designed and laid out plant. Our customers usually split the investment into stages, and we deliver in stages. But in the Czech Republic, we're capable of delivering a large volume, relatively large volume, in one delivery. So delivery is not the end of it, the end of the process. It actually starts the process to some extent, because we also have to guarantee a flawless operations to our customer, because the money is earned by flawless and smooth operations, and every hour generates the income. So we have to be also flexible and able to respond to the needs of the grid, because the grid fluctuates due to the non-stable renewable energy sources. And then the life cycle of the turbine continues to some major repairs and servicing or upgrades and modernization. And that depends on the development of the power plant or the turbine island. And it also depends on the development of the energy market.
In terms of the overall number of installations globally, not all of the units are currently operated. And it's roughly 53 gigawatts installed since 1963. So it's 53 units that would equal to the Temelín unit, one Temelín unit. As I said, the market dictates that we work with the highest installed capacity, but it will also supply turbines ranging from 10 to 12 megawatts. There will be machines on a frame. You would essentially call them a plug-and-play type of devices. You simply come to a site either with a generator or without a generator. You sort of hitch it up, you connect your connections, make your connections, and in a very short period of time, you can get up and running. We're talking the range of RPMs up to 12,000. And when we're talking about machines with the installed capacity of 50 or 60 megawatts, it'll be connected with generators, and with the highest levels, it'll be ultra supercritical parameters in Ledvice, for instance, installed in the Czech Republic, and of course for nuclear power plants. And I can simply summarize what we've developed and what Škoda, Doosan Škoda has supplied. So these are turbines for the former Eastern Germany. After the Iron Curtain fell down, these have been phased out, but our most frequent reference is in Lohisa in Finland. It's a machine by a Russian competitor, and we did a complete overhaul and modernization for the high pressure unit, and we increased the capacity. And we did this on 4 units to the full satisfaction of the customer, Fortum. It was mentioned during lunchtime, at around lunchtime. The first nuclear power plant was A1 in Jaslovské Bohonice, then the units V1 and V2. And currently, there are turbines up and running at the Mochovce power plant, And all the power plants currently operated have been upgraded in terms of the high pressure and low pressure sections, and thereby increasing considerably the capacity. With Mochovce V2, we suppose it'll start to be commercially operated next year. And with the very last bullet point there, commercialization, well, we'll have yet to see, but it's going to be in a couple of years. Dukovany, you could see the delivery periods, 85, 86, and 86, 87, and then 2005, 06, 9, and 10. In Temelín, it was the other way around. The first upgrade of the high pressure unit took place, as you can see here, and then the modernization of the low pressure units took place. I will later show you what was the outcome in terms of the output parameters. And just to give you some visualization of the Loviisa power plant in Finland. And Loviisa obviously is not just the only one, the largest one, but also Dosan has a 10% share in scale in that company. And we also we work together with the supplier of another British supplier of modular and small reactors, that's Rolls-Royce, and also this Russian company that supplies floating power units. We'll see which of these technologies will actually prevail for smaller markets. For these small units is something that will probably see other applications in other countries. However, it's different in the Czech context. We also modernized on some of the units the condensers with titanium pipes. The Temelín upgrade, I can give you more detail about this. We increased we modernized this and increased the capacity by 11 megawatts in the low pressure section, plus 22 in the high pressure section. I'm sorry, there's a typo, it should be low pressure on the first part, LP. So it's roughly 42. And the Temelín power plant is operated in winter months. It's over 1,100 megawatts. And we can also increase the capacity further, the reactor capacity. Just to give you an outline of the solution, the outer body, the outer capsule was maintained, and the inside of it was changed. And within 2 months, the low pressure units were replaced without having a major impact on the operation of the power plant. You can see 1220 millimeter blade that is currently operated at the Temelín nuclear power plant. In the past, the plant room equipment was provided by Skoda Praha plus Skoda Pilsen. We delivered the whole thing for Ledvice, Dosan, Skoda Dosan. The design teams are very often people who still remember the previous projects for Temelín, etc. And I believe it's our knowledge base, and I suppose it is one of our key advantages, competitive advantages. It's a matter of surviving on the market. The new nuclear source in the Czech Republic is another challenge that we are ready for. We've prepared the upgrade for a turbine operating at 3,000 RPM, and we also have a version operating at 1,500 RPM, which is technically easier. In fact, there are certain advantages and disadvantages operating at different RPMs. The one marked as A, meaning 3,000 RPM, is a technology that is well established. It's been operated commercially for over 20 years, so it's pretty well known. Just to give you an idea of the layout, Professor Kolovratník has already mentioned this. This is the traditional solution for 1,000 or 1,200 megawatts. It's a two-flow, low-pressure unit and three high-pressure units. The Temelín configuration is known. We modernized, we transferred the knowledge and experience from Ledvice. Currently, it would be two bearings for each low-pressure unit. And also, we would upgrade the foundation also, but that'll be subject to more detailed discussion if you're interested. At the same time, we prepared as an option 1,500 RPM. We can supply these two configurations, either two low pressure sections or three low pressure sections plus the high pressure section. So directly on site, we can actually provide the blades and install the blades for this, but we are ready to supply this sort of turbine as well. So that is it from me, and if you have any questions, I'll be happy to take them. Thanks for your attention.
Thank you, Mr. Bechlík. And I would give the floor to Mr. Neumann. Mr. Neumann will have his speech. Good afternoon, ladies and gentlemen. My presentation will further elaborate on my presentation last year. It's a presentation discussing a simpler licensing process for research reactors. One of the possibilities, or at least that's what we've been seeing in the media in the last months, one of the options is something that we call a heat reactor. Combination of these two works in Czech, teplátor. So if such a reactor was available and we could pilot test it, we could, for example, provide it with a research reactor license, a simpler process of licensing. Well, usually we hear that Poland does not have any reactor. We don't have to count with them, but they have a national nuclear research center. Not everybody knows about that. It's an Otwok Świerk location near Warsaw, and they have numerous non-nuclear applications connected to their research reactor called Maria. I will show the applications to you later on. This is just a table listing the research reactors, and it's also a comparison of the Polish reactor Maria with our LVR-15. So this Polish research reactor Maria There were actually two of them in the table. Eve is not in operation now. Maria is for heat flows. Maria achieves 30 megawatt output. Well, in the table, there was a slightly different figure, so it doesn't fit from my point of view, but there are roughly 30 megawatt heat flows, and that's important for us. And there are various applications connected to that research reactor. And I'm listing 6 applications on this slide: absorption heat pumps, adsorption coolers, that's for desalination, water desalination, so that's not of interest for us. Then thermal energy storage, that's another application. Then the heating of Maria facility. Then low temperature heat storage and a secondary cooling system. And the last one is a high temperature heat storage with a gas boiler. This is a more detailed description of each of the 6 applications. So the heat pump, well, that's what you saw in the table. So at the bottom, as a footnote, we're just pointing out that there are absorption heat pumps and adsorption coolers. So that could cause some chaos. This is heat output, heat consumption from this thermal plant, Maria, the research reactor. It is similar throughout the year. There are only peaks in winter, of course. And I included this in my presentation because they have been dealing with this for a long time. So even in the times of analog modeling of situations and simulations, they were preparing not only to have this reactor, but also to connect it to the thermal applications. So I have detailed slides for each application. So this is the first one with some cooling units. And you can see that the overall heat output is 930 kilowatt. And the slide shows that there are various types of buildings, and it shows how much they consume: 270 kilowatt, 150, and 170 kilowatt. So there are various types of facilities and buildings. So it is as if you imagine that you're heating a residential complex of blocks of flats. So at the bottom of the slide, when I talked about what I call a depletor type of a reactor, but of course we can consider other types of reactors, energy well, for example. The second application was the one that used heat pumps. So what else can we say? The heat pump works with water, which is somewhere between 12 to 45 degrees of Celsius hot, and it can provide up to 80 to 90 degrees of Celsius target temperature, and the coefficient of efficiency is 1.75. The third application, cogeneration unit with a system of accumulation and cooling, and the desalination, of course, but desalination is not suitable for us, or it's not so interesting for us. So, for example, the middle paragraph, the accumulation of thermal energy and financial return stated is up to 22 years, but that is comparable to the life cycle of the heat pump as it's stated by the manufacturer and supplier. The figures are taken from the Polish sources. So they figured out and calculated how many cubic meters of fuel you save and dozens of thousands of CO2, which never gets emitted. So in terms of heating, thermal heating, you can also heat water. The consumption is 2,978 gigajoules of heat, and a part of it is 2,200 gigajoules can be used as waste heat from Maria reactor. So this picture is just for your information. You could see that it's a channel reactor, and in comparison with that LVR, which is a pool reactor, I just included a number of charts in the presentation. It's probably more suitable for you to look at it afterwards. The presentation will be available to you. So this is one of the ways to handle irradiated materials in the reactor and transport into the hot chamber. This is a chart showing the layout of the fuel channels in the core of the Maria reactor, plus telling you what type of fuel segments there are. This is a scheme of heat calculations. There are various systems, Apollo, Rebus, Tripoli. I do not know these models. I just took it over from the Polish sources. Maybe these are pieces of software that they use in the Czech Republic as well.
This is what the monitor or the screen looks like of the unit operator. You could, again, check the values against what is written in the text and draw your conclusions. I guess the summary of what I'm saying is that a research reactor could be used for also non-nuclear applications. And we said that there are simplified licensing procedures in place for installed capacity below 50 megawatts. So it would be easier to pull it off, and it would also test non-nuclear applications in that way. This is what the reactor building looks like at Świerk in Poland, and this is what the reactor building looks like. And if we had time, I would ask this question. What about the Rzesz Research Center and the Maria Reactor Nuclear Center at Świerk? Compare the two and tell me which one provides more scientific output and which one is larger. Rzesz is 44 hectares. The Świerk is lower. The question is, which one of the two is nicer? Anyway, if you compare the Polish research facility with the Czech research facility in Rzesz, I have to say that our Polish counterparts are more developed in terms of the non-nuclear applications. I'm not saying they are more developed in terms of the research going on at Rzesz. I'm no expert on that, so I'm not saying this. But let me make a note on what the Minister of Industry and Trade said. What he said last year was that there would be city district heating strategy updated in this country. And he said there'll be 3 pillars: natural gas, biomass, and waste. I mean, heat generated from waste. Not even renewables were included on his list. It's taken to be a source of electrical energy. But if you think about photovoltaic panel and thermal panels, then the photovoltaic has twice the efficiency, double the efficiency. So it'll be not necessary to provide electricity and then transform it. So that is, in my personal opinion, the disadvantage, the downside of the new systems being proposed. That's transforming electricity to heat and vice versa. A couple of years ago, we said it would not be efficient. We said electricity was a source of pure, clean energy. So why would you want to convert it into something else? And I believe the PV, photovoltaic panels, could be perhaps used in the heat industry. We'll see. Maybe Polexit, the Polish exit from the EU, might be an issue. Donald Tusk is sort of playing this card, and maybe it's just a political issue and he wants to steal some electorate from his political opponents. Now, as regards the research reactors, you know them very well. There are two in the nuclear research center in Rzeszów. You remember the photo. LVR 15, LR 0, and then there is the Vrabec 1 in Troja, Prague, and Vrabec 2 is in the making in Troja. It'll be a subcritical reactor anyway. There'll be two Vrabec reactors in Prague, Troja. Vrabec 2 is a subcritical reactor, and you electrical switch on and off the neutron transport. So the licensing, that's going to be about 2.5 years, will be much easier than having the Teplator licensed. This was also in the press, and you can see the dimensions there. And you can see the two locations in Holešovice. That's definitely in the downtown area of Prague, so it's more difficult than the research center in Rzeszów because it's outside in the landscape. And they have more advantages, perhaps with the exception of the lower ability to get subsidies. And if we were to connect the research institute in Rzeszów, in terms of the heat supply system, it would be just about 4 kilometers of piping to Třeboradnice, which is the nearest connection point. Thinking about the Teplator project, ČEZ is going its own way in this area. We heard about Energy Well, but there's Allegro, there's Hephaistos at play, and ČEZ also has contracts with Russian counterparts and also with Hitachi, if I'm right, if I know this correctly. I'm not going to read this, but I'd like to share this with you. The Sizewell C unit in the UK will have a non-nuclear system attached to it or tied to it. And you can see that there is a battery storage system, local heating, heat from data centers, also heat energy storage, etc., etc. So that is the site energy cycle, if you like. And that's something that is also becoming to be more attractive for us in the Czech Republic, at least if we take seriously the national strategy. So I talked about the research, nuclear reactors in Poland and in the Czech Republic. And this in the UK is the same thing essentially on a large scale, much larger scale. In relation to the renewable sources of energy, people are talking about wind gas, wind energy turned into electricity, and then you can use it to deliver gas. We could possibly write something like a memorandum to say that nuclear energy should not be discriminated against, because if these things are possible, why not other things in nuclear energy? And this is the nitrogen strategy of the Czech Republic that was approved in 2021. That strategy, that policy document shows this kind of chart, if you like. And what would be interesting to us, people from the nuclear sector, would be listed here in the bluish sections there. But we know that there were a host of strategies that the Ministry of Industry and Trade of the Czech Republic came up with, and nothing really happened in practice. Can be the same case here, but at least we have a strategy, and we have a strategy that is approved. Thank you very much for your attention. If you have any questions, ladies and gentlemen, please go ahead. All right, there are no questions. So I'd like to get back to our steam turbines, and I'd like to hand over to Mr. Šimurda to deliver his presentation.
Tak, děkuji, pane předsedo. Dobrý den. My jsme tu dnešní přednášku vytvořili společně s panem.
Good afternoon, ladies and gentlemen. We prepared the presentation together with Mr. Luxa. So we would like to show to you a simplified model of supersonic flow field in a blade area and the output parts of the turbine profile grid. So I will tell you a few words about the simplified model of the two-dimensional flow field. We will talk about supersonic flow field in between the blades, and then I will show you the sonic curve, and then a few examples of supersonic flow in between the blades. So thanks to a large capacity of computing, we can conduct simulations based on the RAND models, and we can, well, these models are very general, so we can apply them to all sorts of fluid mechanics. But the models themselves do not provide much information on specific problems such as supersonic or subsonic flows. So simpler models used in the previous century seem to be more fitting, because the simplification means that you have to know the subject. The models are good because if you get to know the principle, you very quickly acquire a good intuition for the problem. So I'll speak about a linear potential equation for the defect speed potential. It's a defect speed potential because the potential does not represent an absolute speed, but a change in speed due to a change in geometry. It's a potential equation, so the flow is potential, so it is not, it doesn't have any viscosity, and it's non-spin. So we get to this equation, which is a partial differential equation, non-linear of a second type, and you can see a coefficient 1 minus m square. And that coefficient can be either positive or negative, depending on whether it's a subsonic or supersonic solution. So if Mach is below 1, then we're talking about supersonic flow, and that equation becomes an elliptic equation. If Mach number is above 1, it's a supersonic solution of a hyperbolic type, and an elliptic type problems always have a solution in point P. and it is influenced by the points in the whole area. So the solution is also influenced by all the border conditions. The hyperbolic solution is influenced, and it's again, the solution lies in point P, and if it's a supersonic flow, then it's influenced only by the points on the right-hand side from P, that is upstream points. And not all conditions, not all marginal conditions influence the solution in point P. So in the supersonic solution, you cannot go against the flow. So no point up the stream can influence the solution in point P. So that was an equation that Ludwig Prandtl and Hermann Glauert arrived at independently of each other. Ludwig Prandtl is considered to be the father of modern aerodynamics. I have a book by him, which is very interesting. If you look into that book, you would find out that many later authors used it for inspiration. And to put it into the context of that time when it was published in the times when there was a Battle of Stalingrad. The second gentleman, Mr. Glauert, was also a Briton and a scientist. He looked into propellers, and his equation and his publications were inspiring for the rest of the world. He died very young, unfortunately. In 1934, he was taking a walk with his children in Farnborough in a park, and there were some workers that were demolishing a tree with explosives, and one splinter in that explosion unfortunately hit his head and injured him in such a way that he later on died. So this is a hyperbolic equation with that alpha coefficient, and that equation can be solved using a method of individual characteristics. There are the so-called Mach's lines, and along those lines, small defects expand, and the characteristics can be split into the first type characteristics and the second type characteristics. They flow onto the right side, and we also have a complex characteristics, the expansion ones and compression ones. That method is quite easy to comprehend from the physical characteristics point of view. So when we have a converging area, then we have expansion characteristics of the first type. When we have converging features, then we end up with compression of the first type. Another feature is that if any of those characteristics reaches a flat surface, a flat wall, then it determines the direction of the flow. And on those characteristics, speed changes and the direction of the flow changes as well. So the direction of the flow on the first characteristic, and to compensate for that, you have to have a new characteristics, a new feature of the same intensity, but in the opposite direction to compensate for the first one. So if we have a feature or characteristic which hits a body with constant pressure, then it bounces off with becoming a feature of the opposite direction, but the same type. We have a static pressure, so the complex characteristic or a feature increases the pressure, and to compensate for that, the bouncing off feature is expansion. If we look at the flow field at the last level of a steam turbine of a high output, we can represent it through various cross sections. So we have a heel cross section and the top cross section and the medium cross section. And if you look at the channels in between the blades, of course, the blades have to comply with a certain strength requirements. The heel cross section has very dense grids, unlike the top cross section grids. Because of a high circumference speed, the grid is not so dense and the channel in between the blades is quite short. So we can see that in all cross sections, there's a speed increase up to a transsonic levels, supersonic level, and the input Mach number is above 1, then it's supersonic. But I think that the blade 1220, the input Mach number was just below supersonic levels. So what is important is that that subsonic and supersonic part, they are divided or separated by a sound line or sound border. That's where Mach number equals 1. So it's the speed of sound.
And at the same time, that is the borderline between subsonic flowing, as the elliptical equation, and supersonic, that is the hyperbolic equation. That's why our supersonic, for our supersonic flowing, the sound line is a marginal condition. And the real life shape of this curve depends on a number of factors, like the profile of the blades with different diameters and spacing. We see what the difference is in the space line on the surface layer, and often this is equal to the geometrical shape of the canal. But that is too general a statement. We have more analytical approaches. In this case, there is a simplified geometry. In this case, these are two round-shaped geometries, and if you use the polar system, you will see that this is part of, it's a section of parabola. On the under pressure side, you will get the supersonic flow already ahead of that neck. You can use CFD, which will be a good tool to estimate the supersonic flowing, or you can use an experiment, in this case, optical interferometry. You see that in real life, the lines are similar to parabolic shapes, but the marginal sonic line, the marginal space is also influencing the sonic line. The sonic line really resembles the shape of the geometric neck, which is close to the straight line. Now, let's take a look at what happens in the individual examples. This is a supersonic field, flowing field with the convergent inter-blade canal. And there's a difference between the transonic line, or if it is further in a further curvature, if the curvature continues. This is our colleagues, Mr. Sieverding in 1979. Sieverding did this experiment, and on the edge of the blade, there is an expansion taking place, and the whole output flow is considerably influenced by this edge here. And if you look at this first case, when the edge is slightly curved, there are expansion characteristics on this trailing edge. And these are reflected as expansion characteristics. But at the same time, you've got further expansion characteristics because of the surface. So the expansion is huge. While in this case, where the wall is straight, the trailing edge characteristics are expansion characteristics, but there is no more expansion going on. If you look at the distribution of the Mach number along the dimension here, along the spacing here, where you can see the under pressure part, then the difference in the Mach number is much lower, meaning the output flow is more even. It's more evenly distributed, thereby resulting in lower losses. In terms of sensitivity to the geometry of the profile grid, these are the best examples, with very short distances between the blades. And the whole flow happens between the short part of the trailing edge and the input edge of the blade. The convergent divergent canal is then influenced by the shaping of the blade, and what happens here is the expansion on the trailing edge of the blade, and the expansion is reducing the sonic wave, the impact wave that happens as a result of the flow. If the incoming edge is shaped unsuitably, what can happen is you get an impact wave. You've got the two edges there, and there is a sonic line between S1 and S2. And what happens on the S1 and A1, there is the part of the curve that determines the expansion characteristics, and it becomes a compression characteristic. We said that the sonic line was the marginal condition for constant pressure. So they are reflected as the compression characteristics, and then they interact with the surface of that blade, of the whole blade, and then becomes a compression characteristics. If this is unsuitably shaped, then what you get is a sonic wave, impact wave. On the other hand, if you get a suitably shaped curvature on this input edge, then you can mitigate the impact wave. This is where you can see, I don't know if you can see it, but there is, in this first instance, there is a significant impact wave. And in the picture in the middle, you can see that with the right suitable curvature of the edge, there's no such thing happening. And apart from that, there's also an area of slowed down flowing, because this is based on accumulation. This is 280 millimeters below the top, and at the Skoda 1080 millimeters, and you can see that there's this recompression area developed. And that recompression area develops as a result of the interaction between the sonic line with the surface of the blade, which in most cases is flat or straight, because you use the transonic line. If the blade is curved, then the expansion characteristics that are reflected as compression characteristics are either reflected as expansion characteristics, or they can be compensated by the expansion characteristics that are based on the surface. But if the trailing edge surface is straight, then there are no compression characteristics, no expansion characteristics, and then you get accumulated compression characteristics, and what you get as a result is slowed down speed of flowing. This is an example of the recompression phenomenon in the central section of the 12-20 millimeter blade. The red is sonic line, and the interactions right after the sonic line is where expansion characteristics are taking place. But these characteristics are reflected as compression characteristics, so this is where you get a reduced speed of the flow. The influence of the transonic line has been studied recently. We did it based on experiments with two different grid profiles. They were pretty much the same, with the exception of the transonic line there. The TRW1 was shorter, the TRW2 was longer. With the TRW1, it was a case in which the recompression, the supersonic recompression, does not take place, while with TRW2, where the transonic line is closer to the grid, then the recompression does take place as a result of the interaction.
So you can see it here on this chart with the Mach number. It's interesting that there is an expansion before the compression waves start to accumulate. There is a bigger expansion because of the edge. In heel sections, there's recompression as well, but often the sonic line is moved further into the inner blade channel. The recompression area is not so big. So this is an example of how the whole phenomenon is sensitive to geometry. So this is the whole grid. This is the heel section of blade 1220, and there's recompression. And in some of the interblade channels, there are more major defects, almost as big as the impact wave. The transonic line is often also used for expecting the turbulence and compensating for it to compensate the inner impact wave. So as a conclusion, to understand the phenomena that we can see in the channels, it is good to use the simplified models. It is important to be able to draw the sonic line, and it's important to know that the supersonic flow field is very sensitive to small changes in geometry. And if you use flat areas close to the sonic line, it can speed up the transition to turbulences. So thank you. Any questions?
Prosím vás, pusťte mi první ten.
Would you please go back to the first slide, very first slide in your presentation, that equation? Shouldn't there be a parenthesis? Isn't one part of the parenthesis missing? Yes, of course. I apologize for that. Any further questions? Good afternoon. It's good you paid attention. I wanted to say thank you to Mr. Shimunda and Mr. Lux for putting together this presentation after I I gave them an impulse to do it. Maybe we overdid it a bit, but it is at least an example of showing that knowledge is very important. Without knowledge, you cannot design turbines. And that's why we have the Academy of Sciences and the Thermodynamics Institute. So thank you, David, once again. Okay, thank you too. Now I would like to give the floor to Mr. Škoda, at least that's what's written on my agenda, who should present what we call the Teplator reactor.
Okay, I'm thankful for giving me this great opportunity. Nuclear energy for district cooling is the new idea here. I start with a brief introduction about the novel concept, namely Teplator, which is under design here at the University of West Bohemia. Teplator is a nuclear heat-only reactor, reuses the spent nuclear fuel for district heating application, as you see in this figure. Teplator concept has a vital advantage comparing with the other heat-only ideas. The first advantage is reusing the spent nuclear fuel. So we have zero or maybe even negative fuel cost. No new radioactive waste is produced, and uranium resources are saved. The second feature of this concept is working under low temperature and pressure conditions. So the reactor vessel will be with less thickness, which means decreasing the construction cost. And we can achieve this, the required safety levels with less complicated and costly systems. Teplator technology is modular and compact. Therefore, it can be installed as close as possible to the demand with a small footprint and short construction time. This concept is theoretically optimized for using VVR 440 fuel assemblies and is especially suitable for countries where thousands of fuel assemblies are stored in interim storage casks or spent fuel pools. In this table, you can see the total VVR fuel assemblies that are stored in only Germany plus Czech Republic and Slovakia are about 30,000 fuel assemblies, which potentially is enough for fueling 10 Teplator units for 55 years. Regarding Teplator district heating application, we have compared this idea with different technologies, such as natural gas and biomass-based heating. We see that the generated heat by this concept potentially can be about 50% less than the natural gas or a bit more cheaper than biomass district heating. But Teplator for district cooling, why this concept is introduced here. In this figure, you see the expected amount of required power capacity for increasing the cooling demand over the world. So you can see that the generated heat, the required capacity is estimated to rise by 500% up to 2050, pushing the pressure on the power system. On the other side, here you can see the expected pollution emissions raised from the heating and air cooling sectors, that up to 2091, you can see it is expected to reach about 1.6 gigaton of emissions. Tepplator solution is pollution-free energy and with neglectable electrical energy consumption. So it can be a good solution. Here you can see on the right side of the figure, the current electric-driven approach. Mostly over the world, the electrical cooling, the cooling is mostly provided by electricity. Thermal energy to electrical energy conversion in the power plants, then transmission the electricity over the high voltage, medium voltage and low voltage transmission and distribution grids. Finally, the electricity is converted to cooling energy locally or centrally. But on the left side, you can see the heat-driven district cooling or heating concept. Heat source, such as Tepplator, is installed close to the demand. It drives the absorption cycle chillers for district cooling. And also, the advantage is that during the winter, we can supply the heating by the same district network. So we have investigated the feasibility of district cooling using Tepplator. This figure shows the calculation flowchart from generation until consumption. We have compared these two strategies by determining the energy generation cost, energy transmission cost, the chilling cost, and finally delivering the cooling energy to the demand. For such a long-term planning programming, we need to levelize our demand. So for a typical year, the cooling demand is levelized in 2 steps, peak and average. And on the other side, during the winter, the heating demand also is levelized in 2 steps, peak and average. We have 5 scenarios we have considered using electricity from coal power plant, gas power plant, nuclear power plant, or combined cycle power plant for cooling. And our proposed scenario is using Tepplator plus absorption chilling. In the economic model, we have included the construction cost of the power plant or against Tepplator, the fuel cost, the energy transmission cost, and the chilling cost comparing with each other. And also separately, we have included the carbon emissions. Here you can see the economic comparison between different scenarios. The heat-driven chilling approach, where Tepplator is the heat source, is 30% cheaper than using electricity from gas combined cycle power plant. Regarding carbon emissions, about 2.4 tons of CO2 per each megawatt hour cooling demand is saved per year comparing with the coal electricity using. And regarding saving the electricity, annually about 0.3 megawatt hour of electricity is saved per megawatt hour cooling demand, which means a considerable electricity cost reduction, especially in the hot countries. So our conclusions, the proposed approach for district cooling and heating is an economic solution for these sectors. The unwanted energy conversions and transmissions is minimized. Nuclear energy is a carbon-free and fulfills the pollution reduction targets and without any more radioactive waste. Thank you very much.
Královec. Já mám připomínku.
Hello, my name is Kralovec, and I'd like to ask a question concerning the use of spent fuel. The national strategy of using spent waste nuclear fuel
Dejte mu prosím sluchátka.
There is no problem. I can tell it in English. Yes.
Okay.
My remark is concerned to use of spent fuel.
Yeah.
According to Czech conception, with spent fuel, it's not possible to use it. There are only four possibilities how to handle this spent fuel, or store it, or reprocess it in the outside of Czech Republic.
Yeah.
There is no possibility to use it for energy use.
Okay, so you mentioned that it's not possible from the law side to reuse the spent nuclear fuel. Okay, so this concept is really new and is developed, I think, only during the past 2 years, 3 years, I'm not sure, but so this should be considered probably. Our economic studies show that this concept is potential to reduce the energy generation cost and pollution emissions. So maybe next step should consider this solution. So probably the law maybe should be changed or to give the chance for such a novel technologies.
Can I have a question? First, I have no comments on your economic analysis because it proves that your colleague, Mr. Škoda, despite he's a graduate of reactor department of nuclear faculty, his diploma project was fuel cycle economy. So he knows how to calculate numbers and money. That's all fine. I have only one question, and that's not about the law. How can you technically license the fuel, that spent fuel, for your conceptual reactor? Because your economy would work perfectly if you technically have a solution that really works. You are talking that you want to use a spent fuel. How are you going to license it? What documents are you going to use to the regulator to prove that the fuel that you want to load into that reactor conforms to all necessary nuclear safety requirements? That means integrity, state, whatever is necessary to. How do you want to license the use of such fuel? And no matter where you want to do it, Česko, you can do it, you can try any regulator in the world. How do you want to license? How did you thought in your concept that you would prove the possibility, technical possibility, I mean, to get the license?
Yeah, of course, this is a very will be a complicated problem, but all technologies at the first time, they don't have license. But step by step, yes, with doing research, with doing calculations, and we will proceed with this matter. Of course, it is a really important point and it should be done step by step. We are now during the design process, and what you mentioned will be, of course, in the next, our next work.
No, but you say that you have a solution. You have a solution that is very easy and cheap to implement because you can use existing fuel. You have no idea, I'm sorry to say, a general particular idea in what state this number, can you put back that slide with the numbers of fuel assemblies that you count on? That you have designed reactor for spent fuel of VVR 440 reactors.
Yes.
Do you know where that fuel is now? In what state it is now?
They are between different nuclear power plants. In Germany, Czech Republic, so for example, in Czech Republic, I think it is in Dukovany. They are stored in the spent pools, spent fuel pools.
In spent fuel pool, you have only a small fraction. Most of this fuel is stored in an interim dry storage cask.
Yeah.
How can you prove in what state is that spent fuel after 20 years of storage in dry spent cask? Do you have any idea how you can handle that fuel and load it into a new reactor, put it again into water chemistry, not to mention that I think you're talking about the heavy water.
Yeah.
So how you want to put it into that chemistry, and how are you going to get an approval from any regulator? What can you do? Do you have an imagination? You should have a plan. What will you do to license that fuel for such reactor?
Yeah, of course, there is a plan. And of course, probably my other colleagues or the leader of this project, maybe Dr. Skoda, he knows more about this matter. But the spent fuel in pools or in dry storage, it's possible to be transferred to the location that where we use. For example, this picture shows how to transport this.
Have you ever seen fuel assembly after 20 years of storage in spent fuel pool after being unloaded from the nuclear reactor? And not to mention about the guarantees, how these conditions that were prescribed were maintained. Have you ever seen a fuel assembly pulled out from the spent fuel pool after 20 years of storage?
Me, no, I didn't see it. Okay. But of course, when we are
then
working,
please ask your colleagues whether they have seen it, and ask them whether they would take that fuel assembly, put it in their reactor, and build it next door to their house.
Okay.
Thank you.
Thank you.
I have no further comments and questions.
Thank you.
No more questions.
Okay, thank you. I don't have anything.
Bych poprosil pana inženýra Černého o poslední.
Now I would like to give the floor to Mr. Cherny, who will have the last presentation. The title of his presentation is How to Complete or Not Complete Dukovany Nuclear Power Plant. The not is in parentheses. Good afternoon, my name is Jan Cherny. That no or not in the parentheses means or represents the current situation in the Czech Republic, because we still sort of do not know which route to follow. So I will quickly mention electricity and the energy sector in the Czech Republic, and most of my presentation will focus on the economy, and again, economy because as we know, money always comes first. So electricity as an introduction, how do we generate electricity? Then what is the composition of the energy mix in the Czech Republic? Then a few words about nuclear energy, and then blackout, and then Europe and emission permits. And as for Europe's share on global emissions, Europe represents 4%. So we are trying to save something that we cannot save, in other words. So electricity production, we have three major sources, and that's coal, gas, and oil. Gas and oil is imported, and coal is being phased out and will be phased out soon. Nuclear power plants have been considered to be the main source for the 21st century. We also have water plants, but unfortunately, the water resources in the Czech Republic have been used up to its full potential for energy production. We have renewable sources of energy. Yesterday, we heard from one of the speakers that the O should not represent removable, but let's say interrupted or occasional sources of energy. So nuclear energy, and I originally worked for Škoda, JA. Škoda manufactured 21 reactor complexes of 440 megawatts, 3 complexes of 1,000 megawatts, 2 reactors are in Temelin. One was exported to Bulgaria, and Bulgarians were continuously changing their minds whether they want to put it in operation or not. And then Russians took it away from Bulgaria, so it's not there any longer. What else can be said? All design and construction works, installation, assembling, putting into operation, all of that was done by our own resources in the Czech Republic, and we knew how to do it. Do we really want to move away from all that? I don't know. The nuclear power plant in Dukovany, the first concrete was cast in 1977. Then in 1986, the first 2 blocks were put into operation. It was unique globally because we put 2 blocks in operation during 1 year. All construction costs returned in 8 years of operations. Temelin nuclear power plant, one of the main pillars of our energy mix, energy system. I could give you all the numbers, the hours of operations per year, but I will not do it. Let me say a few words about blackout. Blackout is the threat, the future threat. The 8th of January 2021, when Europe was very, very close to a blackout because power plants in the Balkans were down. And all the experts know that the coal-fired power stations in the Czech Republic saved Europe from blackout. I can mention blackout in India, one of the largest blackouts in the history of mankind in 2012 for 15 hours. 320 million of people were without electricity. I'm also mentioning New York in 1977. That blackout is famous because even the current economic crisis, the economic crisis back then caused a situation when people were plundering, breaking into stores and plundering them, and police was unable to do anything about it shortly after the blackout.
In the Czech Republic, we're doing well. We have a robust network of resources at the moment. And then we have, for instance, here in Pilsen, 3 diesel generators, each of 6 megawatts of installed capacity, so it's 18 megawatts. In Kladno, they have a GT gas turbine with an installed capacity of 43 megawatts. And I believe these sources of energy could operate in an island mode, and they could keep the basic facilities up and running, such as hospitals, etc., etc. And to close my remarks, let me just tell you the funny aspect of the emissions. At this moment, the 1,000 kilos of CO2 is over 60 euros for emission voucher, and it's going up. So it's just redistributing money. There's nothing else. We are taking money away from the coal-fired power plants and the traditional power plants and give the money to somebody who is doing something else and provide the temporary sources of electricity called renewables. What happens next? Everybody is afraid of speculators because they will have a hunch that this is a good chance to make more money. And getting finally to the economic side of things. Here in the Czech Republic, we have the national strategy dated 2004, updated in 2013. Then we have the National Action Plan for Nuclear Energy dated from 2015, and all sorts of other policy documents. And an unnamed vice president of a heat electricity company said about these documents that they are no good, other than perhaps use them as scrap paper. What else then can we do unless and until we have a new national strategy in place? I don't know. We said that we would phase out coal by 2038, and that will already be taking place, in fact, 2030, or perhaps, God forbid, even earlier than that, given the price tag that is attached to the emission vouchers. Speaking about economy, I'd like to mention the example of one very nice power plant. This is Fukushima in Japan. The economic engineers said that to install diesel generators worth $5 million to a site that is nearing its life expectancy. And we all know what happened in the end. A global nuclear tragedy, and particularly a tragedy for Japanese people. Okay, we've covered that. The next point is the tender for the nuclear units in the Czech Republic. The tender process started in 2009. The first bids were submitted in 2013. The tender dossier was really well done, and the bids were so detailed. All of these companies, each of them spent hundreds of millions of crowns to prepare their bids. Despite that, the tender was cancelled in 2014 by the general director of ČEZ, Mr. Beneš. And it was his managerial decision, and that was a correct decision in his logic. The tender was not economically advantageous to ČEZ, of course, the company at the time, because at that time the electricity was much cheaper. It cost 30 euros per megawatt hour. And the national government ambassador, Mr. Mill, said in 2019, said the most expensive electricity is the one that you don't have when you need it. Just to recap, in 2014, we were literally talking about 30 euros per megawatt hour. Today, it's 70 to 90 euros per megawatt hour. And already the outlook for the next 2 years is above 110, 120 sometimes euros per megawatt hour. I don't think it's going to be any cheaper in the future. And the same applies to the emission vouchers. So I don't think there's much to add to these facts. And to close this talk about economics, banks let outflow 300 billion of Czech crowns. billion Czech crowns. Companies owned by foreign companies probably do the same. Nobody really knows how much. The Pilsner Urquell being a good example. They have a new general director, new CEO. He's Romanian, and he's a director of a Romanian, he was a Romanian CEO, and that company was bought by Asahi, and he was now brought over here to the Czech Republic. He said he's got two objectives: cut the cost and increase the profit. And one can definitely understand that as a significant message to the Pilsner Urquell. Then we have the state budget, the national budget. We're in the red figures. I don't think we'll ever return to black figures. It'll be a very distant future. This is due to the pandemic measures, etc. And then the next point, we should have a new tender for the new nuclear unit. And we decided that these would be there'll be three bidders, all of them from abroad. All of the money we invest in this technology, in this tender, will go out of the Czech Republic. And there was one thing that somebody mentioned yesterday. The price for 20 years of maintenance and operation is just about the same as to construct these units. So if we think about 60 years of operation, then we'll spend the next 60 years sending huge amounts of money away from our country. I believe, all in all, it's clear that we just won't have the wherewithal to do it. So if we want to have any sort of facility of this kind, I don't think we can do anything, we can approach it in any other way than the one we used for the previous nuclear projects in the Czechoslovak period. And I believe we need to start to act quickly, because my own calculations say that after 2025, there'll be a shortage of energy, and after 2035, we'll be really lost because we won't have enough energy. And it will be difficult to buy electricity elsewhere because the countries around the Czech Republic, the neighboring countries, will be in a similar mess. So we'll see. And this is literally the closing slide of my remark. There'll be one word that'll become the buzzword. That's self-sufficiency. Food self-sufficiency, energy self-sufficiency. We've lost the first one, the former, and we are insufficient in terms of becoming energy insufficient. And I believe we need to have our own resources, and the only option to go forward, in my view, is to go nuclear. Not just the economic reasons are behind it. There's also the added value of having jobs with great added value. It's very beneficial for our universities, for technical schools, for our students. And that generates a lot of things. I don't really need to list all the reasons. Thank you. Thank you for your attention. Thanks to Mr. Czerny for his wonderful presentation to bring today to a close. Any more questions? Please go ahead.
Which year did you get that figure, or from which year is the figure that the European Union produces 4% of global emissions? Well, the 4% of global emissions being generated in the EU, I don't know which year it's from, but the biggest sources of energy as a country, that's China, India, United States. Well, I know, or I've heard 7 to 8%, but it doesn't change the fact itself. It's a small figure. I think I got the number from the European Union somewhere. I was just interested to know the year of origin. In 2012, the figure was 10%. No, that was last year. I think it's 2020. And we also have to make difference between the European Union and Europe as a continent. Maybe that caused the confusion, but still it's a small figure. Be it 4 or 7 or 8, that's nothing. Any more questions? Okay, then thank you. Thanks to all the presenters, to the speakers. Thank you for nice presentations. And all I can say is see you next year. So let me say thank you to everyone as well. So that was the closure of this year's 2-day Nuclear Days conference. Thank you. Thanks to all of you that stayed with us till the very end. Thanks to all of those that had to leave before the end. And also thanks to all those that watched us remotely over YouTube or other channels. And I don't know whether Mr. Czerny's final presentation shouldn't inspire us to put together, I don't know, something, maybe a declaration or a summary or a conclusion of what we talked about. We had a series of very technical presentations, so it's tough to make conclusions out of those, but many other presentations, like the initial ones, they focused on conceptual issues, the future self-sufficiency, and the last presentation also went in that direction. So we will think about producing some kind of an output. Thank you once again. I'm happy that Nuclear Days made it to the subconscious levels of people's awareness, and we all agree to the fact that without technology, we couldn't have any future at all. So thank you, and see you in 1 year.
Record